this computer.
It's the little round circle on the right-hand side.
Thanks, Gord. You're the best. All right. Okay. I'm going live in 5, 4.
His hair looks good.
Okay.
Just did.
Hey, hi, everyone. I don't know what to say. This is all kind of new to me. Right now, we're broadcasting live. I'm sorry we're running a bit late. I said 7:30. Everyone's here. All my panelists are here. I included Scott Young with us to talk a little bit more about what he's doing with the planetarium and his COVID-19 virus. So right now we're going to have Darren up with his beginner session. This is something I'm really looking forward to it. It's an excellent presentation about viewing planets during the day. So we'll talk a little bit more about it in the, or I'll talk a little bit more about the intro. Okay, so Darren, I'll let you take it away.
Sorry about that, Brian. Okay, let me just grab my screen here. Hopefully everybody can see it. This is
all kind of new to us, so it's...
Yeah, bear with us here. Okay.
And it's all...
I'll redo this here. Share. All right, so I'll do a full screen PowerPoint here. All right, so hopefully everybody can see my screen now. I'm assuming you can, Brian?
Yes, I can.
Okay, good. All right, good evening, everybody, and thanks for attending our first virtual meeting of the year, I guess, and probably one of many until this COVID nonsense gets kind of rectified. So I was going to do the lunar observing part 2, but because of the situation we have with planets right now in quadrature, and I know Jay, I hate taking Jay's thunder ahead of time, but I thought it would be a good idea to talk about daytime astronomy a little bit, and it's kind of in line with what Stan's recent post was on the group site as well, with the crescent moon coming up. So I think you guys will like this one a lot. So I did this on the fly here, and I think this will be a good interim one, and then we'll go to the lunar one next month. So this was the scene that we had a little over about a month, almost 2 months ago now, 6 weeks ago, where we had the moon near Jupiter and Saturn. I know Jay had talked about it, and you know, this is the kind of thing that, you know, a lot of us don't really think about. Why would we do daytime observing other than just dawn and dusk? Well, first of all, the objects are up and invisible, like bright visible now. So why not take advantage of the daylight, especially with this variable weather we have? Sometimes we have some beautiful mornings and into the midday, and then it gets cloudy late day, and then it's raining or snowing or who knows what. And so at least this way you get some astronomy in, which is really nice. At the worst case scenario, you can extend up to 2 and 3 hours of your observing time, or more in some cases, by doing daytime astronomy. So if you happen to have a really nice weather window in your location, it's really nice to be able to take advantage of that and then tie into nighttime and then carry on. You might also catch something that's not visible at any other time. So as an example, like, you know, conjunctions like with the moon and planets in the morning, say, or a slender crescent moon like Stan was talking about yesterday on his post on the group site there. These are the kind of things that you'll miss if you're not doing it during daylight hours. And of course, some events only happen during daylight hours, like transits and eclipses, solar eclipses for sure. So these kind of things are really important, and of course other occultations as well. So this is why we would like to do daytime observing, and I think a lot of people, after seeing this, kind of get an idea of what we can actually do with this. Okay, so here's an example of some daylight observable objects. I mean, obviously the sun and the moon are very, very well-known daytime objects, and we can see them pretty well. Obviously the sun's up during the day as long as the clouds are gone, and the moon is quite frequently available as well. And those make excellent targets to be able to observe. But besides that, we also have the planets, at least the visible planets that have been known since antiquity. The upper left-hand corner there is Mercury, and then Venus is up at the top, Saturn in the middle, Mars, and Jupiter. And you can actually see these planets as they get close to either quadrature or opposition in the case of Mars during the daytime, which is really exciting. The other thing too is you have other objects besides planets as well, like bright stars, Sirius, Canopus. Well, obviously Canopus is invisible from our latitude, but you have Rigel, Regulus. there's a whole range of bright stars that are in the, say, 1 magnitude or brighter that you can take advantage of. I've got an example of a very interesting one near the end of the talk as well. Meteors, I was talking to Brian last night actually a little bit on this talk, and he wasn't aware that you can actually see meteorites hitting the upper atmosphere in the daytime if you go about, say, in a zone between, say, 10 and 30 degrees away from the sun. And if you're in an area where a building, let's say, blocks the sun so you don't have to risk your eyesight, you can actually see these meteorites coming in and hitting the upper atmosphere, and it's really quite interesting. And you might be able to tie a correlation if we're expecting a large meteor shower. If we're seeing some of this stuff during the day near the sun, we might go, you know, maybe there's a good chance that we'll actually have a very good event for a meteor shower at night sometimes too. Very bright comets, obviously we haven't had a lot of them yet. May see something coming up. I know Stan again posted something, and so did I on the website. We may, unfortunately, Atlas has kind of gone by the wayside, but we may see some other bright comets showing up just before they go south in late May. Having said that, you can also, if we happen to get lucky and see a bright supernova or a bright novae, those kind of things are also visible during the day as well. Here's an example of me using my big binoculars for daytime of Venus observing, but you could just as easily use a small scope or even a Daub. And again, at this time, you can see kind of where the binoculars are pointed relative to the shadow of the tripod there. I was about maybe 30 degrees from the sun, and I was looking at Venus in the daytime. This is 2 years ago, mind you, and now we've got an advantage to be able to do daytime Venus observing as well. Now, the best time to observe planets is during maximum elongation or near quadrature. So if we look at the inner planets, or what we call the inferior planets, you cannot get to a position where the sun will be 90 degrees to the object because they never go that far. So Venus has the largest elongation relative to the sun-Earth angle. And I'll talk a little bit more about it later when I talk about Venus observing specifically, but you're around 45 degrees or so. Mercury is closer to about the mid-20s on average. So you have to be a little careful on those inferior planets, but on the superior planets, here's what we have for quadrature. So your sun, Earth, and planetary angle is approximately, well, it is 90 degrees during these quadratures, and there's some advantages to doing that. As an example, for those of you that have gone out on a bright spring day or summer day, you'll notice that this darker band here actually shows up as a natural polarization polarization region. And you can see here, somebody took a photo. You actually have, I think this is Jupiter, or it could be Venus. I borrowed this off the net. Unfortunately, I don't know what that object is, and they didn't have any notes on it. But you can see that you can actually have a little bit darker region here. And this is because the sun's rays are virtually parallel in that region, and they don't scatter nearly as much. And then if you use a polarizing filter, it'll actually allow you to enhance the contrast against the background sky. And you can see here as an example, non-polarized versus polarized. Look at the detail that I have on the right-hand side and using a polarizing filter. One of the least appreciated filters for astronomy, especially for daytime astronomy going. So I really emphasize to all of you, if you don't have a polarizing filter, get one. Not only just for daytime observing, but even dawn-dusk observing. I can extend my observing sessions at least an hour, hour and a half, or longer in some cases, and you see a lot more detail than you would without it. Now, for those of you that have binoculars, I'm just going to briefly mention, Overwork had on their deluxe and above binoculars, something really novel that no other manufacturer that I know of currently does, is they actually threaded their oculars to accept 1.25" eyepiece filters. And I thought that was very cool. But a lot of other binoculars don't have that feature. In fact, almost none of them do. So this is a thing that I did on my end. And so what you do is you roll your eye cups back, you measure the outside diameter. Mine happened to be, for some of my other binoculars, 49 millimeters. And what I actually did is I did an insert cut, and there's Scope Stuff sells a TFA1 that is an 1.25" adapter, and you can actually glue this onto this cap. Now I used a Kaiser cap because it's a little stiffer than the softer plastic caps that you can normally buy on online or that come with your binocular. And this allows you now to have a much firmer cap that'll slip on fairly snugly and then allow you to actually thread filters. So here's an example of what I did here. These are before I did my actual gluing. And you can see I just use a Dremel. If you don't have a Dremel, you might be able to get a friend to help you out if they've got some machining capabilities, but it's fairly easy to cut these out. And then all you do is you just glue them in. So when you have them finished, sorry, the picture isn't the greatest, but basically this is all glued in and perfectly centered. And so here's an example with my APM 10x50s where I can actually clip the binocular filter cell right onto the ocular with the rubber eye caps folded back. And this allows me still to get almost all of the field of view of the binocular using polarizers. And I can just slightly rotate them if I need to darken the background sky. But this has the added benefit for those of you that want to do nighttime observing with your binoculars and do, let's say, looking at nebulae. You could get a set of twin nebula filters and put it on, and it totally expands your ability to use your binoculars for nighttime observing. So there's a lot of really neat features being able to do this kind of thing. So getting to the moon, first of all here, you'll notice that this right-hand image is, this is quite typical in the daylight during midsummer or late spring. And you can see the moon, or really anytime the moon is in quadrature or near first or last quarter. And you can see here how the moon has, you've got a fair amount of detail here, but as soon as we stick a polarizer on, now we've darkened the background sky. Look at the detail I can see and how much contrast I have, especially in the South Polar region here. And also the Maria, they just pop. So again, there's some real advantages to using a polarizer. Even on a gibbous phase like this, you still have, with a moderate polarization, you can still darken the background sky quite a bit. And it's really an advantage to be able to do daytime observing because you want to darken that sky. Now, of course, another object that's always up during the daytime, unless there's clouds, of course, the sun. And there's a range of solar filters for white light continuum observing. I'm very preferable to the Bader Astro solar filter because it gives a neutral white light image here, and it usually tends to distort the wavefront coming into a telescope or a binocular much less than some of the like the full aperture solar screen, say, or there's a bunch of other manufacturers too. And then of course, Thousand Oaks, the glass filters, the Orion glass filters. While they do a pretty good job, there's a lot more detail visible in this middle image than on the right-hand side. So for those of you that are looking at getting a decent solar filter, Kendrick does a good job of making customized solar filters, and you can also get them from Bader, ordering online from a variety of sources that are Bader dealers as well, like the ASTF, which is the Astro Solar Telescope filter, or ASBF, which is the binocular filter. So you can actually get these, and they have a fairly broad range of sizes to accommodate a wide range of instruments. Here's an example of the Bader products on a telescope and a binocular. And you can see this lady here is enjoying the solar views through a larger pair of binoculars there. And again, they're with the binocular filters, they're actually flattened on one side because sometimes the interpupillary distance will require these to get fairly close. So you want to avoid them overlapping or touching. Now, for those of you that want to do kick it up a notch and do H alpha or prominence, or look at some of the more details that you can see in the chromosphere, of course, there's a wide range of filters and full-blown H alpha scopes available as well. So that's another option for daytime observing as well if you have the budget. They're not cheap, but they certainly allow you to do some interesting things. There's a PST, of course, our club has one. So for those of you that are interested in doing solar observing, go ahead and sign it out and enjoy. Pardon me. So going to the planets now from the sun and moon, and again, this is just an overview. We have a typical Venus view here in medium magnifications, and you can see here how this is, this is probably getting fairly right around eastern elongation. You can see how it's pretty much 50% illuminated approximately. The maximum elongation you can ever get is around 47 degrees. On average, it's about 46. So that means that at any given time will see between 45 and 47 degrees away from the sun when it's in a certain part of its orbit, like I showed you before. I'll refer to the diagram in a moment again. Inferior conjunction approaches are best for viewing at low powers, like with binoculars. So right now we have one of those things where we actually have it going from the maximum elongation, and now it's coming towards the sun. It's going to start to get larger and larger and larger. Right now it's about a little over 30 arc seconds in diameter, and it's very bright. So you're going to start to see it becoming more and more of a crescent phase as it approaches towards the region of the sun. And that's a great time to be able to look at Venus in the daytime and in dusk. Again, just for reference, this would be an example of, let's say, Venus, where you have the elongation at about 45 degrees there. So this is where we're right now with Venus, and this is a great time to be viewing it. Now, Mars is another object that can be used, and of course now we have in the late fall or mid-fall, I guess, we have opposition for Mars, and it's going to be a pretty good one. With a telescope, you can actually get some pretty decent even daytime images as you go away from elongation or maximum elongation, or in this case, superior conjunction, or where it's in full opposition. As it starts to get towards quadrature, it's still relatively large, say a month or two either side of its opposition, and it may be visible during some of the daylight hours. It could be late dusk or early dawn, depending on what side of the opposition you're getting. And again, in these situations, it's going to well exceed -2 mag, in some cases almost -3 magnitude. So with a polarizer and a telescope at medium powers, you can actually start to still be able to view the detail on the planet, which is really exciting. And it rivals Jupiter for brightness at this time. Of course, with Jupiter is one of the brighter objects in the sky. I would say it's the fourth brightest object in the sky. And I find that generally Jupiter is a great target to do play around with if you want to cut your teeth on doing daytime planetary observing. Besides Venus, is because of the fact that it's so large and bright on average. So I find normally if you're using a smaller aperture, like say an 80 millimeter or something, usually between 60 and 90 power is a good starter range. So if you have an eyepiece that'll give you in that range, that'll be very good. For larger apertures, like in the, say, 5-inch and above, 130 power is usually a good starter point. You can go 100 to 130 to get started, and then you can go up or down depending on how bright the object is and the sky conditions that you have and the transparency. Details in binoculars, I find generally with Jupiter, definitely using polarizers, you can pull out a lot of this band structure. When I use 25 by 100 binoculars, I can see almost everything that's in this image for sure, including the great red spot when it's a little darker, like it has been lately. Last year, I was able to find it as it goes across the transit, and it was not hard, and that was still well before dusk. Like it was just starting to get into early dusk, and it was visible, no problem in the 25s. But if you have a binocular that's even 16 to 20, you can start to see quite a bit of banding detail if you can employ a polarizer. And again, the only way to do that with most binoculars that are out there is to use an eyepiece mounted polarizing filter cell that I talked about a few minutes ago. Now, Saturn's a really interesting target because a lot of people don't realize that, especially at other parts in its orbit, this one might be a bit of a challenge for some of you, but as we see it starting to rise and get out of the southern skies and kind of into more reasonable declinations, you'll be able to see it higher up in the sky towards the south as it approaches quadrature and so on. But this is not atypical using a reasonable sized telescope, like in the 5 to 6 inch range even. You can sometimes do in the 130 to 150 power range. This is probably like a C8 minimum. I'm thinking it's a C9.25 image here. Now, they didn't polarize it here. This would be a small aperture or a high power binocular view. But even here, you know, it's really neat because Saturn has this sort of ghostly ethereal view to it. And you can see quite a bit of detail as well. Like you can see Cassini division, obviously the crepe ring isn't available, but you can see quite a bit of banding. And if you choose your magnification and your filtering levels properly, you can actually see quite a bit of detail on the planet even during the day. And it's quite exciting. That's really best around, say, 10 degrees either side of quadrature, for sure. Tends to be very, very effective way of viewing this planet. So certainly for those of you that are interested in doing this, give it a whirl, because you could be very pleasantly surprised. And a lot of people don't think of Saturn as a daytime object at all. And you can see on the left-hand side here, it almost looks ethereal. When you're starting to realize that you're looking at a planet, you know, 1 billion or more kilometers away in the daytime, that's pretty cool, I think. Now, Mercury is always proximal to the sun. Its elongation never varies more than, say, on average, about 23 degrees or so. So the furthest it'll go is 28, and it depends on where its orbit is relative to when we catch it. 18 degrees is very typical sometimes too. So it's never in true dark. So be very careful when you're viewing Mercury proximal to the sun. Make sure you take the appropriate precautions. You can be well rewarded. And with a telescope, this is obviously like a low power view here. Just looks like a tiny dot, not too impressive. But with a telescope, say running in especially at dusk or something, and you have a reasonable angle with the ecliptic, like we get sometimes at certain times of the year, like say right now in spring, it's not too bad, but in the fall, sometimes we'll get some pretty good views as well, the ecliptic being a little bit more angled, and therefore even at moderate elongations, it's still available for at least an hour after sunset. This is a good time to pull out your telescope and take a look. Depending on the seeing, I mean, you might actually see some nice phase relationships with it as it approaches an inferior conjunction, and it can be very, very rewarding. So again, don't give up on that little nearest planet. It can be very, very fruitful. Now here's some tips and tricks. This is just a few that I came up with. Definitely, I've been pushing polarizers a lot. So, pardon me. Use polarizers whenever possible. Certainly, it darkens your background sky regardless, whether you're in quadrature or even at other times, it'll still darken your background sky, which will give you more contrast and more general detail. I definitely recommend marking infinity focus on binoculars, or note your telescope focuser where it's very close to infinity focus as well, if it doesn't have a graduated scale, or preset it and leave it, because you're going to need to do that for daytime observing, especially if you're using an alt-az mount. With a motorized go-to mount, you may not have that same issue, because even if the planet is in the field of view, you can just tweak it with the focus and then you're good. But if you're trying to visually pan, I know Stan and I'm just trying to remember who else. Oh, Bill Crosney had mentioned that make sure that you set your optics to near infinity, so that way you don't want to be panning manually across the sky, let's say with a crescent moon or a super thin crescent moon, because you'll go right past it. You need to have that critical focus very close in order to be able to capture the object in the daytime, especially if it's a dimmer object like Saturn or Mars, when it's not too close to opposition, or even Venus. Sometimes it can still help you. Use wider field initially if you're using a telescope. Start around, the middle ranges, say around 40 to 50 power to start with, and then once you've got the object, then go ahead and pump up the power and balance it based on your own preference and your ability to see detail. And again, that'll vary with seeing and sky conditions. Certainly with binoculars, for those of you that have 15 by 70s or up, you're in good luck, because that'll help you a lot. That doesn't mean that 10 by 50s aren't useful instruments. So those of you that have 10 by 50 instruments, you can still benefit from doing planetary observing, but obviously you're going to be limited to the amount of details and how close the moons are from, say, Jupiter as an example. Just for those of you that are not aware, even in general dark sky conditions, even a 15 by 70, a good quality 15 by 70 pair can show some of the brighter moons of Saturn, especially when they're in the far part of the orbit or maximum elongation from the planet. You can actually see down to, say, those ones that are around 10th magnitude, like Hyperion, iapetus, stuff like that, they are visible depending on the conditions and so on. So definitely don't give up on your binoculars if that's the only instrument you have. Definitely go and take a look at it because you can see an amazing amount of detail. It might take some practice, but again, it's really exciting. Definitely use, if you're using a go-to mount, I like to use the sun or the moon to align if it's up, to do an initial solar system align and then slew to the object of interest. If you don't have a solar filter, you may want to leave your overnight setup and hibernate the mount and then wake it up in the morning and then go ahead and do your daytime observing. Totally up to you, and it'll hinge on the weather conditions, of course, as well. For Alta systems, you can use a planetarium app and an inclinometer or some other way of measuring the altitude to help you find the object. So here's an example of a digital inclinometer, a very inexpensive one that's available on eBay, or there's other variants of these on Amazon and so on. They're only about, they're less than $15 US, but they're very handy. And you can even use them to help align your scope if you've got, let's say, a go-to mount and you want to get your, sort of pre-align your latitude angle. You can actually use these for that as well. Very, very handy. And then, of course, for those of you that are using either binoculars or wide field telescope, you can use these as well. Turn them on, set them on. It'll give you an approximation, but given the field of view of a wide field telescope or a low power bino, you should be able to find planets fairly easy using this. It'll certainly be in the field of view if you're bang on once you've used an app to find, evaluate what altitude a planet's at. So say it was at 26 degrees, you could set it somewhere around 26 and it should be pretty close into the field of view. You might just have to pan and azimuth a little bit to find it. Definitely mounting helps in this case. Now, for those of you that have binoculars, one of the biggest beasts I have, I guess I could say, with every manufacturer of binoculars, except for about one or two of them, is the fact that they never mark infinity focus or even have a graduated scale for distance. There's a few manufacturers that do out of Germany. I know of one, Minox, for some of their higher end ones, but it's a real pain in the butt. They assume that this thing's going to be used for a wide range, and that's fine. But it would be nice to have at least an approximate infinity mark on there. So you can actually do something like what I've done here. And I recommend you doing this. You can get modeling paint like an acrylic enamel paint, or if you have a craft paint, just take a toothpick and just, as long as it's acrylic enamel one, just lightly dab the tip, and then predetermine your binoculars at infinity. And then when you bring them in, before you put them away, just make a mark maybe in the middle of the wherever your maximum or optimal interpupillary distance is that you're going to have, and mark that as well. So usually there'll be a mark here and then a couple of graduated marks, or it may actually have a graduated scale, 70, 80, 60, 70, 65, so on. I still like to put a little dot where it's at, so that way I can, even if I share a pair of binoculars, I can get back to where I was very, very quickly. And it's especially critical when you have higher power binos, because that interpupillary distance can be really critical. But for those of you that want to do daytime planetary observing, this is a great way to preset your binoculars, because you're going to be in the neighborhood. And so when Bill was mentioning about looking for these slender crescent moons and pre-focusing to infinity, this is what he's meaning. But this way you can get there without having to take them out and look. And you're almost bang on, and you should be able to find a thin crescent moon with those. I do that with all my binoculars. Now, besides the planets and so on, I mean, there's other objects that are visible during the day. Obviously, I talked about bright comets. Those of you that are a little older may remember Hale-Bopp in '97, so that was 23 years ago. And it was definitely visible for, even as an early dawn object well into midday when it was doing its near swing. And that was a lot of fun to look at because it had a pretty sizable tail. Of course, Comet McNaught was another one. And especially this is going into the southern hemisphere. I was able to bang it off with binoculars pretty easily before it went south. And then a lot of you may have seen Comet McNaught images online with huge fantails. And they were very fortunate down in Australia and in the southern hemisphere because they got a really nice show. We're overdue for a nice view up here. So I'm hoping that one of these comets, it seems like we're seeing some more coming through now, that are expected to exceed hopefully 6 magnitude or better. And I'm hoping one of them will really wake up and give us a nice treat, but to be determined on there. But these comets, when they do start to have a bright coma and a bright nucleus, and then they have a decent tail, they're visible during the daytime with binoculars as well. So a lot of fun viewing that. Now, for those of you that want a real challenge, especially with instruments in the 6, 8, and beyond range, with a go-to mount or a good tracking mount, Epsilon Lyrae, this is an example of a fellow that took a photo here using a C6 in the daytime, and you can see the date and time there. So it was in the fall, almost winter, and it was mid-afternoon, and he got the double in there. That's a pretty good image. So some of you astrophotography aficionados, I challenge you to do something like this. I would really like to see some of these images. It doesn't necessarily have to be the double, but if it could be a normal star, or it could be like something like, well, Sirius is going to be going pretty soon, but maybe Regulus, or if there's another target that you have in mind, I would really, maybe a brighter double star that you could do, maybe Alberio or something like that. I think that would be really neat to see. So I challenge all of you AP enthusiasts to kick it up a notch. I think this would be really neat to see what you guys can do with your equipment. So I'm dropping the gauntlet, and I'm hoping you guys will pick it up and impress us here the next time. This is an example of Regulus in the daylight with a 110 millimeter refractor. And again, this is a daytime image. Now, this guy didn't use a polarizer, but can you imagine how nice it would have been with a polarizer here? It would have been really nice. So again, you can do bright star observing with your telescope, especially in the daytime. And a lot of people don't think about that. So I challenge all of you to seize the day, especially with the planets now. Right now they're in quadrature or very close to it. I definitely recommend that you follow the planets as they rise in the morning and go into the daylight. If you have a tracking scope, or if you can take the time, especially with this COVID thing, doing backyard astronomy, this is a great way to do it, especially when we can't do some of the star parties we want to do. Thanks, guys. I have time for maybe 1 or 2 quick questions if somebody wants to ask something. Go ahead. No questions? So I guess everybody got that just fine, or I bored the heck out of you. I'm not sure which. So, all right, thanks, Brian. Just before I go, I just wanted to mention, for those of you that are in the mentorship program, or that are interested in joining, because of this COVID thing, obviously we're going to have some challenges being able to get out to Birds Hill and do organized events for the near future. So we're going to, I talked to Brian about it and some of the council members, and we're looking at doing some virtual ones. And what I'll be posting on the website an actual little blurb on it. And what we'll end up doing is I'm going to ask an initial question: is what topics would you like us to focus on early part of this year? And then we'll start addressing those. And we might do a combination of live video as well as maybe some YouTube videos that can be clickable links and so on. So stay tuned for that. But in the meantime, those of you that do have my email, if there's some things you want us to focus on in the spring, let us know. Okay. Well, that's it for me. Thanks, Brian.
Okay, thank you, Darren. That was very nice. I'm gonna have to get myself some polarized filters for my telescope. Anyways, we'll move along.
And camera.
Camera. Right.
Yeah, don't forget cameras too.
Cameras too. Okay. All right. What we're going to do is I'm going to. Where's my? Okay, so I might keep this going because our time's a little bit short. I want to keep it as short as possible for everyone. I just want to say thank you for joining us. This is kind of new for us, especially for me doing Zoom webinar. So there might be a few little problems here and there, but so far it looks like it's running pretty good. I have asked Scott to join us. He's not on the slide, but he will join us and explain more about what's going on with the planetarium. So we had Darren, we have Jay Anderson following after my intro, then we have Michelle, and then we'll have Scott Young. Then we'll take a short 5-minute break, and then we'll do Jerry's presentation. But what's different with Jerry was he pre-recorded it because of his limited bandwidth out there. But it's an excellent presentation. His slides are just great. You're gonna love this. Also, too, we're going to end hopefully around 9:30 or so. And then at 10 o'clock, I'm going to try this. We're going to try a virtual Boston Pizza, like more like an informal meeting. So hopefully we should have, with this national account, I'll be able to host up to 500 people if I really wanted to. Well, we'll see how it goes. I want to give this a try, an actual meeting, not a webinar, but an actual meeting. So we'll move on. Okay, so just kind of mention a quick point here. Because the COVID-19, of course, Old Comic March is still closed. I confirmed that with Jacques. The Loaner School program is on hold. And at our last council meeting on Friday, we decided to close Glen Lee for just because of that. We didn't want to have the virus spread, so we decided to shut it down. Of course, Scott will explain more about what's up with the planetarium, but he's got something nice lined up, but I'll let him explain that. Danielle did pass me some slides about what's going on with the university. Even though the open house is closed for the moment until it's until further notice, they do have something lined up for them. If you notice down below, there is a link to their website, and they do have some interesting videos for people to show. One of them is, of course, meant for kids. It's only 20, 30 minutes, but you know, if you have some kids, it'd be great to check it out. Also, too, we do have another video for all ages. Again, just go visit the website, and we'll keep you informed on what's going on with the University of Manitoba. Next, because of we have this new Zoom program, we want to do more Zoom. Try and keep it normal for everyone because of this you know, social distance that we have here. Of course, Darren did mention about the mentor programs. We'll have something lined up for you, and of course, he will mention on the website. Of course, we're using it for our council meetings. We'll do a question and answer where people can just put up questions, and we'll have our panelists answer it as best we can. I'm going to try a virtual star party. Hopefully that's going to work out, but we'll see how that goes. Again, we'll have more programs lined up for Zoom, and we're going to schedule this because of this COVID-19 and the Zoom, and of course everyone would be home. I was going to do a little bit more RASC meeting, like the Zoom that we're doing right now, but keep it shorter. So we'll have one maybe for May 1st, but we're only going to keep it for 1 hour. So stay tuned for that. We'll do more of that. And of course, like I mentioned before, I was hoping, and we'll give this a try, we'll do a member site, but it's going to be a Zoom hosting kind of thing. So that will be interesting to see how that's going to go. So I think that's all I have to say. So stay home, stay safe, and I'll pass this on to Jay Anderson.
Well, good afternoon, everybody. 51 of us or something like that I see on the list. So what we're going to do now is share my screen, and we'll go over to talk about what's coming up. Unfortunately, there's some interesting stuff tonight, and it looks like it's going to turn cloudy. So let's get over to where we want to be here. And we'll start this guy up. There we go. Oh, who'd have thought we'd do this? Also, I got the date wrong on this, so that's what happens when you borrow. So we start with tonight's Southern Horizon. We're looking at, looking at the departure of the winter Milky Way on one side, and we're looking at the arrival of the realm of the galaxies out there on the left-hand side. You can see that I've marked in some garish pink colors some of the more prominent Messier objects. And we've mentioned these before many times, this lovely little group of clusters over in here in Auriga. And of course, the Beehive cluster, which is pretty much only a binocular target because it's so big. So between these four and this guy, you've got some good observing in the evening in this region. And Venus, of course, Venus we'll speak about in a few minutes. And then over in this part of the region, in the bowl of Virgo, right in here, we have the Virgo galaxies coming up. Now, I'm going to skip out of this for a minute and see what I can do with my trustworthy, speak to me, oh great computer. Here we are, lined up for this evening, April the 18th. Well, maybe a day in advance. Starting out at 9 o'clock in the evening, and I'm just going to play the sky as it goes by overnight, except that my controls, okay, they're still visible in the screen. So here we are, getting darker. Here's the winter Milky Way fading away into the sunset, realm of the galaxies, some in Leo here and the other ones in Virgo in here.
We can only see PowerPoint.
Oh, Judy tells me you can only see PowerPoint on this. Brian, is that right?
Yes, I didn't want. I thought that's what you wanted.
All right, well, I guess we can't do that one then.
Yeah, you can. Sure. You just have to select when you do your share screen. You have to select the app that you or the program that you want to show or feature
before I share it.
That one.
Oh, okay. Well, that's possible.
Just
So let's just keep going on this thing to where we are anyway. So take my word for it, the sky will move because there's a couple other things I want to show here that'll refer to the morning. Okay, here we go. Current planets. Sun has no sunspots today as usual. Mercury is up in the morning sky now, but it's headed in for the sun, and anything in the morning sky in the way of planets is actually pretty poorly placed because the ecliptic is at such a shallow angle coming up from the horizon there that nothing rises very sharply the way it does in the evening sky. And in the evening sky, we've got Venus in now sinking back toward the sun, so it's past its greatest elongation, but it's also getting bigger. And so right now there's a kind of competition between Venus becoming more and more of a crescent, but at the same time getting bigger and bigger. So it does increase its brightness for a while before the shrinking crescent takes over and begins to reduce its intensity. You can see up here in the upper right, I've got the April 17th appearance of Venus and its relative size. And then a month later, you can see how much of a crescent it's become. And in fact, it'll be on the middle of next month, this time next month, it'll be 45 arc seconds in size. And the human eye typically has a resolution of around 50 arc seconds. So those of us with good eyesight, which does not include myself, can actually see Venus as a crescent, which is interesting because you have the opportunity to see both a crescent Venus and a crescent moon at one time during the month. Mars is also increasing in size. You can see that at the top center, the difference in sizes, not as dramatic as Venus, but its size is only 7 to 8 arc seconds. As we get into the later part of the year, Mars will get an awful lot bigger. It's got a magnitude of about +1, so it's not really dominant, but its red color is pretty appropriate and pretty obvious in the morning. So it's relatively easy to pick out, even though it is low down in the sky. You get into Jupiter, it's pretty easy to spot. Bright in the morning, getting higher. It's toward the middle of next month, it goes into retrograde motion, which means that it's going to be starting to move back towards Saturn, which is on its left. But at the same time, Saturn also goes into retrograde motion. And this is just they appear to move backwards in the sky because the Earth is passing them. Anyway, Jupiter moves in retrograde more quickly than Saturn does, so they will eventually catch up with each other in a couple of months and pass very, very close to each other. And that'll be a major event when it comes along. So they're not very good for viewing because of their low altitude in the sky, but they're the highlights in the morning sky if you want to be up. And of course, if you watch them in daylight, you can switch easily from one to the other. Uranus is pretty much lost for us. Oh, I forgot to change March. It's actually the conditions for April and May, but I forgot to change the dates there. And Neptune's coming out from behind the sun, and that one really has to be in dark of night before it becomes any kind of a decent target. Interesting aspect of the Milky Way. This is a scene for tonight, looking toward the north or northwest. And in this case, this is at 3 a.m., if I'm not mistaken. And the Milky Way will lie sort of parallel to the horizon. And you can go online and find pictures of people that people have taken showing this. And it's actually quite an attractive way to present the Milky Way. But you can also see, if you know anything about your constellations, that that's a huge span across there. It goes all the way from the southwest to the northeast. So in order to take a picture like that, you have to take 3, 4, 5 pictures in a line and make a panorama up, which is not very hard to do because you don't want to be tracking this. You just want it to be a stationary camera. So you're talking, you could get this whole set of pictures in about 3 or 4 minutes, and nothing would move so far that you wouldn't be able to put together. Instead of this virtual panorama, a very real one. The big trick, of course, is finding a place where you can look straight north or almost straight north in the dark. And you probably want to go to somewhere along the shores of the lakes to the north so that you can get a good view without anybody's lights in the way. Another thing Stanis talked a lot about is crescent moon. He mentioned the 23rd coming up as a good opportunity to pick up a crescent moon that's less than 24 hours old. 23 and a half, I think he says. And so what I've done is given you a set of kind of pictures of the event. You can see that at sunset, I've turned off the sky in the program. So sun is setting and the moon is in here. Moon's 5 degrees up at that time, or almost 6. And the sun is at this position. You can mark where the sun is in the landing because you won't see the moon right away. And suggests about 16 minutes later in here, you might start seriously looking for the moon. And by this time, it's 3.5 degrees up. And it's at azimuth of 285, so it's 6 degrees to the left of where the sun sets. So you should have a good idea where your binocular field of view is. Probably go about 2 fields over to the left, use some marker along the horizon, then go straight up and look for the moon. Prime time for looking would be 25 minutes after sunset, but now we're down to a little over 2 degrees altitude. Well, 2 degrees altitude is 4 times the diameter of the moon, so you're basically 4 moons above the horizon here. And we're now at 287, so you're even closer to your position of where the sun set, or the precise point. And finally, I've shown it here, 1 degrees altitude. With 33 minutes after sunset, that would be a challenge at 9:06 in the evening. Here's what it'll look like. Very, very thin crescent here. Now, normally you'd use a fast exposure for a moon, but when you've got this small a crescent, this low down, you'll have to use a relatively slow exposure. Stan suggested 1/4 second for the parameters he had set in his camera. Ones I would typically use, you probably shoot about 1/100th of a second. But on something like that, you would be bracketing. The main challenge is just to see it visually. And for that, probably having your binoculars on a tripod would be a good idea, so you can really examine the sky in the area where the moon is to try and spot that thin crescent. On April the 26th, we have the moon passing under Venus. Here's an image of it here shortly before sunset, or shortly before moonset. You can see a lot sooner than that, but a vista like this looks a lot nicer if you can frame it with something in the foreground. So this is actually at 11 p.m. If you were to go out at 9, you'd see it a lot higher in the sky, but without the pretty picture aspect to it. And then on May the 13th, we have the gibbous moon passing underneath Jupiter and Saturn, which are getting close together. Jupiter, they're now gradually converging so that they will meet each other probably right in about this point sometime in the future. And then 2 days later, the moon will be fatter and it'll be passing under Mars. But you can see the angle of the ecliptic here is very, very shallow. Whereas here in the evening sky, it's quite a bit more obtuse angle, which is why conditions are better for observing planets at this time of year in the evening sky, and why these guys never really get very high up. We have the Lyrid meteors reaching a peak on the 22nd, but they have a range of about a week on each side of that. Not very many of them, 10 to 20 per hour. RASC handbook says 20, some of the websites say 10. But the moon is very good because the peak comes 8 hours before new moon, so you essentially have no moon in the sky for these things. On the 27th, the moon's under the Pleiades, but they're not very close. It's nothing like last month's passage. May 8th, we have the Eta Aquariid meteor showers. That's a very low down in Aquarius. So it has a very, very broad peak, again, for a week on either side of maximum, and has a higher rate, but we don't see them as well. You can see that this example from Sky and Telescope, which is more in tune with American observing conditions, the radiant would be lower in the sky for us. But still, with a rate like that, it's probably well worth seeing. As far as the Lyrids are concerned, they're pretty good for us because the radiant is relatively high. And you wouldn't be looking right at the radiant anyway, you'd be looking off to one side. Comet Atlas is breaking up. Here's some pictures from several days in April, beginning on the 1st and with the 15th. Darren said it was fading away, but it's fading away in a rather spectacular fashion. You'll find a number of decent photographs of the pieces of the comet. So this is a good opportunity for anybody with a camera and a telescope to try and catch pictures of the breakup. You can see the light curve over here on the right. The brightness has started to turn down, but not really rapidly. Certainly still a good target for a telescope and for just watching a comet break up into pieces, something that you won't, although it happens frequently, you won't get to see it very often, so well presented as this is. Comet Pan-STARRS is up around 7.8, so it's actually slightly brighter than Atlas, and it's circumpolar as well as Atlas, so the two of them are together up in the sky. Again, an easy target for even track mounting and on a long telephoto lens. We still have a little bit of time while this is at its brightest point, so certainly a month or more where you can go and play with this one. But what's interesting about these two comets, Atlas and Pan-STARRS, is where they are right now together in the sky. This is circumpolar because the North Star is up in this area, Cassiopeia. So these are at their low point in the daily cycle of the stars as they swing around the North Pole, but you could go out there at 3 a.m. and with a relatively modest lens, I don't know, maybe 135 millimeter or something, be actually able to photograph the two of them together. But looking out the window here, nobody's going to get a picture of these two guys tonight. And this one is headed off this way, and this one's headed off this way. So tonight is actually about the closest that they are together. Interesting little, just Comet Swan, brand new one discovered on the 13th and 7.9 magnitude. This is the one Darren mentioned that looked like it might get pretty bright. It's now circumpolar and moving down toward the north horizon. But here we have a graph that shows its brightness predicted and its visibility from the northern hemisphere. And you can see that when it's at maximum brightness, it's just barely popping over the horizon in the northern hemisphere. and it's not until we get into August that it starts to come up. But by then it's down to magnitude 12. So this will be an interesting comet. If it gets as bright as 3.5, then coming and looking for it up against the horizon, and this will not be for 50 degrees north, but anyway, coming up and looking for it, this will be something to watch for, because we have seen some really spectacular climates that are very close to the horizon in the past. And if this one surprises, then it could be a surprise. So we'll look for that in late May. And here's the cat, the constellation Felis, that was in existence for a very short time. So thank you all very much.
Okay, well, thank you, Jay. That was very nice. Okay, moving right along. I don't see, we'll start with Scott next. I don't see Michelle. Okay, Scott.
I'm here. I'm here. I'm under your name for some weird reason. I'll see if I can share my screen here. Let's give this a go.
Sorry, Scott. Okay. Yeah, I saw my email, like, I'm here twice. So anyway.
Yeah, I'm going to try to share. Do you see the slideshow?
No. It's funny because you were there earlier too, so.
One second. Oh, maybe I have to, okay, maybe I'll stop sharing first and try it again.
Okay. Okay, that's good. You're there.
You see it?
Yeah, I
you see my mouse?
Yes,
okay.
I do.
Okay, good. Right. Okay, I was gonna try and turn on my picture, but I'll leave that, like break something. Okay, so this is my first virtual presentation of what's new. And this picture is of Venice after people in self-isolation. And so here I have before and after pictures, and apparently, so these are taken by a satellite. And you can see the pollution has actually dropped significantly in Venice and in fact in Europe. So I thought that was interesting. Well, not quite what's new, but it is a satellite image, so it's from space or whatever. Okay. So I revisited this object that came from interstellar space called Oumuamua or something like that. I forget the pronunciation. And since then, researchers have looked at this and tried to figure out its origins. So the interesting thing about this thing is they once thought interstellar objects were more like comets and should give tails when they come through the system. But it turns out that this comet, as well as, or I should say comet, this object, like most of the interstellar objects, don't have a tail. In fact, they presume it's dry or something like that. And in fact, it's also very dark. It absorbs a lot of light. So they theorize that the other problem with this thing is that it's very elongated, and most objects, like in an Oort cloud, are more spherical. Like they don't have a flatness ratio of 10 to 1. So they expect that this might have been a fragment of a larger object around some early solar system somewhere else, where it was broke up by tidal forces, just like Shoemaker-Levy 9 with Jupiter, if you recall that event. So this breakup kind of explains the unusual shape, and they figure it happened near its host star. So that could have actually charred the surface, outgassed it, and in the process, that outgassing actually accelerated out of the system. And in addition, it sort of sealed in the rest of if there's any ice water inside. So this is kind of the theory they have. And they figured that a lot of objects like these pop out of other systems and fill interstellar space. So there could be a lot more objects out there, and people are looking for them now because we're more and more looking at near Earth objects and stuff like that. So we're picking these up. So expect to see a lot more. Okay. So next thing I just looked at was Sagittarius A star, which is the black hole at the center of our galaxy. It's about 4 million times more massive than our sun. And there's I believe it's on an episode of How the Universe Works. There's a good episode where they show how they track all these objects. They use infrared because there's a lot of clouds in the way. You can't really see the core optically. And so the diagram here just sort of shows the orbits of all the things they've been carefully tracking. And for example, they have a star called S2, which is traveling about 3% the speed of light around the suspected black hole. And it takes about 16 years to do an orbit, and we've been studying these for almost 2.5 decades. And here I just remind you what the speed of light is. Whoops. Well, okay, let's go back. It's 300,000 kilometers a second. And so 3% is 9,000 kilometers a second. And if you compare that to our sun going around the core, it's 230 kilometers a second, just to give you some ideas. So the interesting thing about this is normally in Newtonian physics, planets follow an elliptical orbit, not a rosette pattern, which I'm showing on the next slide here. So on the left, you can see a simulation of Newtonian mechanics, how it would be for normal elliptical orbit. However, what's happening with the star is it's doing this rosette pattern. And this is is explained through the theory of general relativity. It's very similar to the precession of Mercury's orbit, where there are general relativistic contributions to why its orbit precesses. Although it's slightly more complicated than that because the sun contributes, the oblateness of the sun and the other planets also contribute to the precession. So this is yet another test of general theory of relativity, showing this precession due to the large mass of the black hole. Okay. So next I looked at NASA. A bunch of scientists tracked shock waves of a supernova B906 Carinae. And this is just sort of a diagram showing the shock waves coming out from a nova, which I'll explain on the next slide. And initially, the expansion starts like this, a thick ring, and then roughly 10 days later or so over that period, the shock waves come off from the surface of this neutron star, probably due to some delayed nuclear type of interaction. And this then presents itself in gamma ray and X-rays, and you also see a visible light here. So they used 3 satellites, the Fermi Gamma Ray satellite, the NuSTAR X light. My mouse is very sensitive. And then the Bright Toronto optical satellite. And what they found is that these objects are actually very bright in the X-rays and gamma rays, much brighter than they thought. And so there's some energetic process going on here with the shock waves that are actually have significant more power than the rest of this. And these then translate into a visible spectrum across the shock wave. So a lot of the energy is being dissipated from this object through the shock waves. So this is Nova Carinae, the V906. And I don't know yet if you can see the animation, but you can see it brightening over and then dimming over the period of a year. So that gives you an idea of the time scale of the event. And just to review, or maybe it's review, basically you have a white dwarf star and then a regular star or red supergiant orbiting it, and the gas is being stripped off into the star, and then when it reaches a certain threshold, it causes a nova, and some novas repeat. So, that's sort of the process. So that diagram you saw there was this nova, and I managed to get an animation from NASA and just clip out that portion of it. So this is an animation showing the nova explosion, and you can see the outer shell here. And the shape of that shell is due to the orbit of the neutron star and the host and the red giant. So that's what's giving it that flatness. And then you can see the gamma ray and X-ray emissions, which happen, they say, about 10 days later. So that's sort of showing you. And then a lot of the energy is being dissipated in these lobes. So you can see infrared and then gamma rays. So then the last thing I looked at was, it was actually interesting. You can actually measure the wind speeds in gas giants and brown dwarfs. For instance, Jupiter, you can measure the wind speed using infrared to look at how fast the clouds are moving. And using radio, you can measure rotation of magnetic field, which gives you the core rotation of the object. And what they found is that on Jupiter, the clouds actually move faster than the core, and that's due to some complex dynamics between the gas and the core and some other stuff. And so they actually did this measurement on a brown dwarf. It's called 2 mass J whatever. This is actually just the coordinates. And 2 mass was this large survey done by many telescopes over the full sky and infrared. And so this is just a designation of one of the objects. And so basically they wanted to study this object, so they used the Spitzer Space Telescope and measured the upper atmospheric winds, and then used a very large array telescope, radio telescopes, to measure the rotation of the core. And what they found is the atmosphere rotates about 600 kilometers a second compared to Jupiter, which is 100 kilometers a second. And the other interesting thing about this is that they could potentially apply these applications to certain exoplanets. There, though, the magnetic fields are weaker, so they'd have to use more sensitive, lower frequency telescopes, but there's a possibility. Okay, so that's essentially what's new. Are there any questions? Someone could try.
I have a quick question for you, Scott. Darren here. On the rotation there, you were saying that they're monitoring magnetic fields, but are they actually using Doppler measurements in order to get the wind speeds? For the most part?
So the article wasn't clear, but that's what I presume. I can't see you doing it any other way. So there has to be a Doppler effect. So for that to happen, there has to be a certain
So the
size.
magnetic field is really kind of irrelevant from the perspective of the rotation rate. I mean, not that that doesn't impact things somewhat, but I'm assuming that the main, if you're using planetary rotation as the main, using spectroscopy or whatever with the Doppler, that's going to give you a lot more information, and then they can speculate on the magnetic field based on the distribution of the velocities, I assume. Huh?
Well, presumably the magnetic field itself would also be rotating and extended beyond the star. So you should be able to see that in a radio telescope. It's called a polarization measure or something like that. It's a rotation measure. Yeah, so it should get a rotation measure, which is going to give you the speed of the core. And the reason you get the magnetic field is due to electrons and stuff that's generating the field from the core. The clouds, I would presume, I would presume you get the clouds. I would presume that's also a similar Doppler type effect or shifting in the spectrum. So
I'm assuming as well with some of the Juno data on Jupiter, they're going to be able to use Jupiter as sort of obviously a failed brown dwarf, but that acts as kind of a template, just like we do with solar dynamics, trying to extend our knowledge based on what we know and have learned and observed elsewhere and locally. and kind of tie it all together, right? So I assume that they're going to use
Yeah.
Jupiter as a template for that somewhat.
Yes, in fact, that's what they said. The modeling that they've done is consistent between that and the brown dwarf. So I found it interesting that we could actually measure that in a brown dwarf that's not very far away. So, yeah. Any other questions out there in the ether? No?
We do have a
Okay.
question from the chat here. Bob is asking, any better idea what Jupiter's core is like?
I don't know. I'm not a planetary expert. So maybe there's someone in the audience who knows.
Well, I'm not a total expert, but from my understanding, they're talking about the possibility of possibly metallic hydrogen, and as hydrogen
Yes,
compresses, that's what they're thinking. So I think once Juno's done its final run, and then finally pummeling into the atmosphere, I think we'll probably have a lot more data on that, and then we'll have a better idea, because it's going to take them a while to basically take that data and then analyze it properly. I think, it's given us a wealth of data, not only visual, but magnetospheric. So I think that's probably what's going to happen. And then they'll probably refine the data. What is I'm trying to remember, do you know, Scott, when Juno's going to be done? What is that, 2022 or something?
Schedule. Oh, I think the mission's scheduled to run until.
Oh, sorry, you cut out. Scheduled to run until when?
I think the mission is scheduled to run till 2022, but we'll have to see what happens in terms of, they tend to extend things as often as possible. I know they don't want to keep it out there indefinitely because they don't want to run into Europa or cause any kind of contamination. But
well, not only that, too, it's
everything
being subjected to a lot of radiation, too. So I'm pretty sure at some point, as well as they've tried to shield it, I'm sure the electronics are going to start to degrade at some point, too, if you extend the mission. So.
All right.
I think you're going to have to kick me off. I can't seem to find my Zoom.
Okay. What I'm going to do, I'm going to pass it on to Scott. I think Scott has control.
Oh, here it is. I found it. Okay.
Thank you.
Okay, I think I do have control. Let's see here. So hi everybody, I'm Scott Young. I'm the senior planetarium producer at the Manitoba Museum. As you can guess, we are closed. This is actually day number 35 for me. Although I do still get weekends, but it's been a long haul. We closed down the 13th.
Scott, just so you know, your audio is kind of muted. It almost sounds like you have your microphone either too close to your face or something. It was really good before, but it's kind of gone away.
Okay, thanks. How's that? Is that better?
Much better.
Okay. How bizarre. So yeah, we are closed, but we are much like Danielle's note about the University of Manitoba's planetarium. We are going online. The Manitoba Museum at Home is launched last week, and we're doing everything from online question and answers. We're running.
You're fading again.
Okay, the microphone hasn't moved, so I'm not sure what's going on. We have
It's much better now.
Okay. There we go. We started producing star stories with Marvin to try and get some astronomy content out there for all the kids that are that are all missing out their field trips. Marvin, of course, is our venerable Zeiss planetarium projector that you see there, and Marvin is older than 50 years old. The museum building is 50 years old this year, but we've put off any of those celebrations. So there's a series of videos on our Facebook page and on YouTube as well. But we're really starting to get into live. This Zoom program is pretty cool to do webinars and meetings and things like that. Our staff has been meeting constantly. And we've got a couple of Facebook Live events coming up. This Wednesday, April the 22nd, is Earth Day It's actually the 50th anniversary of Earth Day. So right in the middle of the 50th anniversary of the Apollo missions, Apollo 13's 50th anniversary of landing was today. It's no surprise that Earth Day started up right after the Apollo missions hit, and all of those great pictures of the Earth from space came back and gave people that sense of the fragility and the thinness of the atmosphere. So we're going to be running some special programs there. We will have some live streaming of solar observing. We have a PST as well as a white light filter. And I've also got this great thing that I got when I was a little kid. It's a solar cooker. So basically it's a parabolic mirror with a stick on it where you put your hot dog and you can cook hot dogs with the sun. So I'm going to be making hot dogs and talking a little bit about the sun and Earth and climate and so on. And we're also going to be running 2 planetarium shows. Evans and Sutherland and Spitz, the companies that make the planetarium programs, are really supporting the planetariums. We're all closed, of course. We're not making any ticket revenue. And I know for us, ticket revenue is about 50% of our budget. So things are tight. And rather than charging us for these shows, all these suppliers are just letting us run them. So it's really, really great. We're going to be running a show called Dynamic Earth, which is the show that we would have been premiering this summer had we been open. Instead, we'll be running it online. And we will also be running a show called Zula Patrol Down to Earth, which is a kid's show. Not quite exactly, it's the same characters, but not the same show that Danielle listed for the U of M planetarium. So that's coming up next week, and that's really going to be sort of our big systems test for International Astronomy Day. Saturday, the 2nd of May, first quarter moon. We're going to be doing some things in the daytime where we do astronomy activities. We're going to show people how to build planispheres so that they can make their own star map. We're going to show them how to make a dipper clock to figure out the time and so on. We're going to do some moon phase demonstrations, might even do the toilet paper model of the solar system. We'll have to see. And then that evening, we'll be doing some live streaming of images from telescopes. If anybody's interested in joining along on any of these events, just drop me a line. Particularly for Astronomy Day, it would be great to, if any of you have the capability to do a Facebook Live event, even just from your phone, held over the eyepiece or whatever. It would be great to have a multitude of places where people can look at, we'll have the great first quarter moon. Venus will still be up. It's hard to get too much else there unless somebody has a really good camera and is going to take some pictures. But that'll be kind of exciting. It's a totally different way to do astronomy for us, obviously. But I was at first thinking, well, this is going to be really, really hard. I'm not going to have my dome. But of course, I have the real sky instead, and everybody else has it too. So I think this is a really good opportunity for us, all of us as astronomers, science communicators, to get people back and engaged with the real sky again and looking up and just seeing all the cool stuff that's out there. I might even be persuaded to lighten up on the supermoon and promote that and see what happens from that. So if you are interested, you can sign up, subscribe on our Facebook page, facebook.com/Manitoba Museum. We're on YouTube, we're on Twitter, we're on Instagram. But quite frankly, Facebook is the one that I use the most, and I'm running a lot of these events, so that's the place to check in. The museum side, all my colleagues are also doing other programs. We've got a program on the Winnipeg strike. We have a couple of other courses that are available for people to sign up for. So we're trying to do as much as we can while the museum is closed and still get out there and do all of these things. So again, if you have any questions, I'd be happy to answer them. And let me see if I can get back to Zoom here. There we go. Let me see. Just realized nobody saw any of my slides, did you? Okay. We'll just go to the one slide which will provide the 2 dates of things. Can everyone see that?
Yes, we can.
That is out. Okay, good. So yeah, it's kind of exciting for us, and hopefully we'll see you online. And if again, any telescope folks that are able to do live streams, I'd love to hear from you, and we'll hook you up. I think that's it.
Okay,
Thanks.
thanks, Scott. I think
Yep.
we had one question here. I saw a hand up. I'm getting a lot of experience here. Sylvia, I think I saw your hand.
Oh yeah, I was just gonna say I couldn't see Scott's presentation.
Yeah, that was because Scott forgot to press the share button, which is hilarious because yeah, I had also closed the chat window, which apparently we shouldn't do because I didn't see Gord warning me saying, "Hey, I can't see your screen." So tech support's only good if you listen to them. Okay, thanks a lot, everyone.
Okay, thank you. All right. Okay, what we're going to do is we're going to take a short, maybe 4 or 5 minute break, maybe less, so I can get Jerry's presentation. Jerry, did you want to say anything or?
Jerry
Okay.
doesn't have a microphone, but Jerry said that if anybody had questions, they could send them via email, and he can answer those questions on the email.
Okay, that's even better. Okay, all right. What we're going to do is we'll take a quick 5 minute break. We'll reconvene at 9 o'clock here, and we'll do Jerry's presentation. I need a little cup of coffee here, so I'll see you guys then. All right.
Thanks, Brian.
that to X.
Jerry, are you able to hear me? Okay. Anyways, okay, we're gonna start with Jerry's presentation. Okay, so how does this work? Okay, okay, so, all right. Okay, so it's 5 minutes. I hope everyone's back. All right, I'm gonna start sharing the screen. I have his presentation up. Okay, here we go.
On April 26th,
You want to turn your volume up.
marked the 100th anniversary of the great astronomy debate of 1920. The debate addressed issues that had been argued over for over 200 years. Some of the ideas had been in vogue and then out of vogue and back again over that period of time. Just as the Copernican revolution showed us our place in the solar system, the results of this debate showed us our place in the universe. The origins of this debate can be traced back to the great German philosopher Immanuel Kant. His first idea, the nebular hypothesis, was an idea he got from Emanuel Swedenborg. It's the idea that you could start out a universe with clouds of material that under gravitational attraction would eventually condense, start spinning, and eventually end up evolving into planetary systems. It also allowed you to talk about the ways in which larger structures might also be formed by this same process. The second idea of Kant's was the idea of the island universe. This idea he got from Thomas Wright. The island universe theory states that all those little faint lenticular objects we see in the sky are actually galaxies equivalent to our own. Many questions arose as to the nature of the island universe theory, such as how big or how little are these objects? Are they very close to us? Are they further away? What was their composition? Were they made out of stars, or were
Sorry, that's my fault.
they made out of other materials such as gas and dust? Further questions such as exactly how many types of these objects were out there, and the ultimate question of whether or not they were like the Milky Way were some of the issues that plagued the island universe theory. There are two general trends in science. One is to make broad generalizations about a group of objects. Another approach is to analyze and categorize various objects within groups. This is known as taxonomy. Here's some sketches of various objects observed by William Herschel. And you can see his attempts to try and put them into categories. Here's ones that had bright central nucleus. These ones over here had lenticular forms. Some of these were without categorization. And of course, there's all sorts of questions that we can ask about these objects. Were these nebula objects composed of stars? Were they composed of gas? And when we finally recognize some of them to be spirals, what was the role that they played in all of this? The first people to address this issue of the size and scale of the universe was William and Carolyn Herschel. Their first task was to describe the size and shape of the galaxy. Previous astronomers had thought that the stars were just randomly distributed throughout the sky. But William and Carol Herschel recognized that this was not the case and that there are some places where there are far more stars than others. They developed a procedure for trying to describe and investigate the way in which the galaxy was formed. They called it stargazing. And what it involved was taking a telescope, pointing it at various parts of the sky, in this case, 683 different points of the sky, and just counting the number and types of stars there. Since they assumed that all stars were quite similar to each other, fainter stars were assumed to be further away. So by pointing their telescope at various places across the sky, they were able to measure, in some sense, the shape of our galaxy. You can notice in this diagram, which was done by William Herschel in 1785, the general shape that he determined for our galaxy. Notice right here the location of the sun, rather close to the center. He described the resulting shape of our galaxy as being an irregular millstone. And here's a picture of William and his sister Caroline supposedly conducting these observations. They show Caroline in the role of a secretary and recorder of information, but she was as much an observer of this enterprise as William was. The next step forward was taken by Friedrich Bessel, who in 1838 finally managed to measure the parallax of a star. Measuring the parallax of a star involved being in a particular position and seeing the star against a certain background group of stars. Then waiting 6 months later till the Earth was on the other side of its orbit and looking again to see which stars were in the background of the target star. Doing simple trigonometry at this point allowed you to determine the distance to that star. For the first time, we were able to measure the distance in this fashion. 6 years earlier, measurements had been done by Thomas Henderson of the star Alpha Centauri. But for some reason, he never bothered to reduce his data and publish it. So the credit for all of this goes to Friedrich Bessel, who did it with the star 61 Cygni. This is Bill Parsons, or more formally known as William Parsons, the 3rd Earl of Ross. And this was the Leviathan, the giant 6-foot telescope Newtonian reflecting telescope that he had built to observe the skies from central Ireland. As you can see in this picture, the cloudy skies of central Ireland was probably one of the better days that he had for these kinds of observations. The telescope used metal speculum mirrors at this point. He had 2 of them made so that he could always be observing while the other one was being cleaned or otherwise repaired. You can see the giant mount that he needed for this telescope. Here's the stairway that you use to climb up to the catwalk, where you move the telescope back and forth and observe from someplace along this precarious ledge. Being a very large reflector allowed him to gather lots of light and observe some of these very small, faint nebula, such as the nebula seen here as he sketched in that wonderful pointillist style. This is the Crab Nebula, Messier 1. And for the first time, you might be able to see why it got its name. Parsons was the one who actually named it the Crab Nebula. And having this shape, you can see why he thought it should deserve such a name. But more importantly, for our purposes, is the sketch he made of the Whirlpool Nebula, Messier 51. In this, you can definitely see the spiral structure of the nebula. This was the first time this was ever observed, and it allowed people to finally recognize what was going on with some of those lenticular nebula that they had been observing. The Leviathan telescope was used for many years afterwards, but not so much by Bill Parsons himself, because being the Earl of Ross, his attentions were required elsewhere, because 1848 was also the first year of the Great Irish Potato Famine. Other observers did get to use his telescope and did observations with it up into the early 1900s, but it wasn't used all that much. It was a rather unwieldy beast. It was eventually melted down when metal was required for war purposes. One of the new technologies to come along was spectroscopy. This was the ability to make a spectrum of some of the astronomical objects with the purpose of trying to analyze the materials that would be found within them. This was generally described by Gustav Kirchhoff's 3 laws, where if you had a light source, such as a star, it would give you a continuous spectrum. If there was a gas cloud that was relatively cool in front of a light source, you would get absorption lines. This could also happen from the atmosphere of a star. Hot or excited gas states would give you emission line spectrums. The Huggins, William and Margaret Huggins, were 2 people that went off to investigate some of the spectra of these faint nebulous objects, such as this object right here, which is the Cat's Eye Nebula in Draco. This is an image from about 1913 of what it looked like, and it had the spiral shape, so they thought they were investigating the spiral nebula at this point. Here is a drawing of the spectrum that William Huggins observed when he looked at the Cat's Eye Nebula. And as you can see, it's an emission line spectrum that has various lines here, including this one peculiar one, which he didn't recognize from the spectra of any of the known Earth substances that would give this line. He dubbed this line here Nebulium, named after nebulas, because it seemed that this was the only place that this line appeared. It didn't appear on earthly substances. The interesting and obvious conclusion of all of this is that spiral nebula look as if they have emission line spectrums, which means they're not composed of stars, they're actually gaseous in nature. This was one of the nails in the coffin on the idea that the spiral nebula were made and composed of groups of stars. Few people know about Andrew Ainsley Common. He was born the son of a doctor who made his fortune taking over his uncle's plumbing business and becoming a sanitation engineer for the city of London, where his company built much of the waterworks of the city. But his real passion was for astronomy, and especially combining astronomy with photography that was just becoming available at the time. He was one of the first people to take advantage of the new technology of being able to apply silver to glass to make mirrors. And his telescopes were of the Newtonian reflector style that used glass mirrors for their main objectives. Here is a picture of the back of Andrew Common's house. You can see his roll-off roof observatory here, quite reminiscent of some that you can find even to this day. This is an 18-inch telescope that he had made for him after trying his own 17-inch that didn't work out so well. But he soon was able to combine the latest in photography techniques with his passion for astronomy. And in 1883, he was able to take this picture of the Orion Nebula. It was the first picture that showed details deeper than what you could see visually through the large telescopes at the time. And this won him the Royal Astronomical Society of England's gold medal in 1883. So in some sense, Andrew Common is the founding father of astrophotography and deserves to be better known. He also was one of the first people to suffer from aperture fever. This telescope here is his 18-inch telescope that he had set up. It didn't satisfy him for long, and he soon wanted a larger one and commissioned the same company that made this one to make him a 36-inch telescope. That telescope he sold off because he was getting them to make a 60-inch telescope. And by the time that telescope came along for him, the skies in London were getting to be so bright that it wasn't worthwhile to make use of such large instruments in the city of London. His 36 instrument was sold to Ed Crossley to become what is known as the Crossley telescope in North America. His 60-inch telescope eventually ended up down in South Africa, where it was set up in an observatory there. So even though Andrew Common didn't do much in the way of further observing, he certainly was a person that gave us an incredible amount of technology to work with, and his pioneering efforts in astrophotography set the stage for what was to come later. The island universe hypothesis was quite popular during the early and middle 1800s, but by the time Herschel had discovered a few more peculiar instances where some of his nebula started to look as if they were gaseous, and then combine that with the ideas that we had from the Huggins that apparently were looking at what looked like a spiral nebula and showed to have a gaseous emission line spectrum, support for the theory began to fade. And by the late 1800s, things had died down to the point where they had thought that they had sort of sorted out much of what has gone on in this debate. We have this wonderful quote from Simon Newcomb, who states, "We are probably nearing the limit of all we can know about astronomy." We also have a quote from Agnes Clark in 1905. She was kind of the Bill Nye science guy of her time. And she wrote, "The questions whether nebulae are external galaxies hardly needs discussion. No competent thinker with the whole of available evidence can maintain that a single nebula to be a star system of coordinate rank with the Milky Way." This was the general prevailing idea at the turn of the century. But despite Newcomb's warnings about the end of astronomy, a lot of exploration was still going forward. Up here we have a picture taken in the early part of the 1900s of the Harvard Observatory in Peru. This was set up there to take a look at the part of the sky that we don't get to see from the northern hemisphere. Down here, we have a picture of the Crossley reflector that had been given by Crossley to the Lick Observatory in the United States, in California there, to be set up and used at their new observatory. It turned out to be a real miserable instrument to use. The mount was a disaster. But along comes James Keeler here, who was employed at Lick, and he was given the task of trying to make this scope work right, and redid the whole mount, made it into a rather useful instrument, where he started taking pictures such as this little picture here. And this long-term astrophotography effort proved that the number of spiral nebulae that are out there are way, way more than they had first suspected. Here's a picture of one nebula right here in the middle, but all of these arrows on these pictures here are pointing to other spiral nebulae in the picture. So James Keeler decided that there was much, much more to be done on this subject and started a project going forward. He was also one who was rather convinced that these spirals were probably not connected to our galaxy. Unfortunately, he never lived long enough to make this exploration go forward. Down in the lower left here, we have a picture of the 60-inch telescope that's being hauled up the sides of Mount Wilson, again in California, as part of the new observatory that was being built there. One of the main influences on the debate and discoveries that were made in the 1900s was due to the increase in technology. Here we have a view of the 60-inch reflector that was mounted in up on Mount Wilson. It was the first of a whole series of instruments of larger reflectors that was soon to displace the older style refracting telescopes of the earlier years. Both of these institutions at Mount Wilson and at the Yerkes Observatory were due to George Ellery Hale, who approached astronomy from a different point of view. He wanted it to be a more integrated approach between astronomy and physics, and hence you needed a building such as the wonderful Yerkes Observatory here that combined both observatories for telescopes along with astrophotography labs, with spectroscopy labs, and everything else that was needed from the physics side of things to apply to the data that the astronomers were collecting. The astrophotography side of things was developing as well. Here is Edwin Hubble at the large plate camera for the 100-inch telescope. And up here we have a view of Vesto Slipher. We'll be hearing more about him in a little bit, where he is at the controls aligning his spectrometer mounted on the telescope in Lowell Observatory in Flagstaff. A special note in all of this talk of technology has to be Mount Wilson's 100-inch reflector. This is a picture of it here, all mounted at this point in its dome. Wasn't even supposed to have a dome. George Ritchie, the designer and optician behind this telescope, didn't think it needed a dome and thought it'd be better if it was just behind a big, high metal fence. But a dome was constructed for it. And here's a picture of it, how it looks today. But this telescope had a troubled history, even though It is probably the one instrument that's responsible for more in the advancement of science than any other telescope we've had, and that includes Hubble to this day. Here on the left is a picture of the cross-section of the mirror that was involved in this telescope. Here's the mirrored surface on top, but you have to draw attention to the glass of which it is made. So you can see it was poured in 3 separate layers, and it had developed bubbles in between each of these layers. When George Ritchie, when we know him of Ritchie Chrétien fame, of the design of the telescopes that a lot of us like to use for astrophotography, when Ritchie took a look at this mirror, he said, "This thing is junk. This thing is not going to be made into a mirror. It's going to break before we even get it hogged out." It was a piece of glass that he thought was just totally disastrous for the job. Both Hale and Ritchie took trips over to France, the only place that had kilns large enough to cast a 100-inch mirror, and tried to get them to make new mirrors. They had new furnaces, new kilns, but none of the mirrors that they came up with afterwards were any good. Most of them broke during the cool down process, which takes a very long time to do. So eventually what happened was Walter Adams and George Hale decided, we're going to go back and take another look at this mirror here and see if we can't use it. They eventually convinced Ritchie, against his better judgment, to grind it out and shape it into the mirror that it is, and it eventually was installed in the telescope for use, and it turned out to be a rather good mirror after all, which makes it all the more surprising because you realize this glass that's being used to make this mirror is old recycled French wine bottles. The science of the early 1900s was quite exciting and quite innovative. Here we have a picture of the Rutherford Bohr atom showing the way in which they thought light could be emitted in very narrow frequencies, explaining the emission line spectrums. We've got Albert Einstein here explaining to Willem de Sitter some of his theories. And I think this period is best summed up by Willem de Sitter himself, who said, "Never in all the history of science has there been a period when new theories and hypotheses arose, flourished, and were abandoned in so quick succession as in the last 15 or 20 years." He said that in 1931. Here's a picture of Arthur Eddington, who in 1919 went out on that eclipse expedition that verified the results of Einstein's general theory of relativity. So 1905, you had Einstein's miracle year where he had all those papers on the photoelectric effect, the special theory of relativity, and within 15 years, 14 years, you've got his general theory of relativity being subjected and passing its first test. Work was also being done trying to describe the size and shape of the Milky Way. Here is the early attempt by Cornelius Easton to sort of repeat what Herschel had done with his star gauging measurements and get a better picture of what our Milky Way galaxy should look like. This is the first time we see evidence of people ascribing spiral type structures within our Milky Way. This was reinforced in 1904 by Jacobus Kapteyn, who plotted many of the closest stars to our own, showing that there was these distinct star streams, as he called them, and which we now interpret as being part of the Sagittarius arm, the Orion arm, which contains us in here, and the arm outwards, the Perseus arm. So this was decent data for which to start speculating on the shape of the galaxy. This picture below is a later attempt by Cornelius Easton to try and describe the Milky Way galaxy. And notice how much it has evolved, this picture has evolved from his earlier attempt. In both cases, note that the sun is not at the center of the galaxy, it's off to one side. The main action of the galaxy is taking place up over here. In this picture, his sun is located right over here, whereas the main center of the galaxy is found off in this area. Now, the question is whether or not to consider his observations. This one was done mostly with visual telescope work. This one was combined from a bunch of photographs from all around the world, because he needed pictures of more complete pictures of the sky. But he readily admitted that this isn't necessarily exactly a bunch of plots of stars. So it isn't raw data in that sense of the term, but is sort of something in between. It's based on what's there. It gives the general shape, but in no ways did he want anyone to consider it to be an actual plotting of stars. And part of this is revealed to us by the fact that in his earlier work, the center of his galaxy is found in the direction of the constellation Cygnus. Now, this is quite understandable because Easton was doing his observations in Holland, and at that northern latitude, the brightest part of the Milky Way to us is that bright patch in the constellation Cygnus. So sort of natural for him to assume that this was a good candidate for where the center of our galaxy lay. When he gets to this later view, he doesn't seem to be able to purge himself of the idea, because he still has the center of the galaxy off in the direction of Cygnus. So this constitutes relatively good data about the positions and size of our galaxy, whereas Easton's work has to be taken with a good grain of salt. And one could easily assume here that at some point Easton is being influenced by the shape of spiral nebulas to go from this data to this data, where it takes on the natural look of a spiral nebula as he would have become familiar with in that time. So was this a case of his theoretical notions of what he thought was going on out there influencing the way in which he was collecting his data? There's not enough evidence to say one way or another about that. Another aspect of astronomy that entered into the debate was the classification of stars, where most of the work was being done by the Harvard Observatory. Two of the main characters that were involved in classifying stars were Henry Norris Russell and Einar Hertzsprung. Together, they contributed to what we now know of as the Hertzsprung-Russell diagram. That's a modern version of it shown right here. This chart allowed them to start speculating as to how stars might evolve and how to identify certain stars in the sky that were going to be useful in determining distances and motions and all sorts of other aspects of the stars that they were studying. For instance, one of their early ideas about what was going on here was that stars all started off as large, giant, cool stars that through contraction eventually moved up along the lines, becoming hotter and hotter and hotter, reaching a point at which its fuel started diminishing and it was declining down through temperature and size as it used up its fuel until it ended up as a very small, cool star. This idea of this form of stellar evolution was eventually rejected, and a totally different interpretation was given to the Hertzsprung-Russell diagram. But it was interesting to see the way in which they were struggling to try and make sense of everything that they were coming across at this point, and how they needed to identify, for instance, the large red giant stars from the red dwarf stars that also seem to show a very similar spectrum, because the two, being so different in size, lent themselves to being totally different in brightness. And brightness was one of the main factors they used in measuring the size of the galaxy. Henrietta Leavitt was one of the Harvard computers, a group of women, most of them were astronomy graduates, who were hired on to process the huge amount of data that was being brought in from observatories all over the world. Henrietta Leavitt's work involved documenting the variable stars, especially those found in the Small Magellanic Cloud. One of the things she discovered while she was documenting these variable stars in the Magellanic Cloud was a particular kind of variable that's shown in this graph here, where the star would have a particularly slow decline in its brightness and then suddenly regain its brightness over a period of time. And it was she who first noticed that this period of time between, say, the two troughs or two peaks corresponded to the star's brightness. The reason she was so sure that she was comparing stars naturally without a distance problem was, again, she was looking at the Small Magellanic Cloud. All those stars were assumed to be pretty much more or less the same distance away from each other. So a star that appeared dimmer to her probably really was dimmer. And when she noticed that the dimmer variables, such as those found down here, had much shorter periods between brightness peaks rather than the brighter stars, she realized that this formed a kind of relationship where the brighter the star, the longer it takes to go through one of its cycles. So you had a period versus luminosity graph that you could calculate at this point. This allowed you to get at the real true brightness of certain stars just by looking at the period of their variation. This became an incredibly important measuring stick for us to apply to the rest of our galaxy to measure distances beyond what we could do with parallax. Parallax measurements were only good out to about 300, maybe 400 light years tops. We needed something to measure distances much greater than that, and Cepheid variables proved to be something that might give us this new measuring stick. Her brilliant idea couldn't be written about by herself. She was just a hired gun at the Harvard Observatory. So what happened was, when it came time to publish this information, her boss, Edward Pickering, had to come out and actually write the paper. She wasn't allowed to do such. So her paper had to be introduced by him with something along the lines of, the following statement regarding the periods of 25 variable stars in the Small Magellanic Cloud has been prepared by Miss Leavitt. And then what follows was her paper, and then it was signed by Edward Pickering. Meanwhile, at the Lowell Observatory in Flagstaff, Arizona, Percival Lowell had hired Vesto Slipher to investigate the spectrum of the Spiral Nebula. His interest in that is understandable enough, in that he was very preoccupied with planets, especially the planet Mars, and all of his investigations into whether or not there could be life on Mars. So he hired Slipher to investigate the Spiral Nebula in the hopes that it might shed some light on the formation of planets in accordance with the nebular theory. To get himself going, Slipper did spectrums of the various planets. Here we have his spectrum of the planet Saturn. You'll notice that the absorption lines have a bit of a slope to it, and this is to be expected. They had understood the Doppler effect and how it had affected spectra, and the planet Saturn is rotating, and it's rotating at enough speed that there will be a shift in the lines. In this spectrum, this is the blue end of the spectrum, and this is the longer or red end of the spectrum. So that meant that this part of the planet Saturn was the part that was rotating towards you. This part was the part that was rotating away from you. In the case of the ring, this ring with its sloped line up here was rotating towards you, whereas this one, further down towards the red end, was rotating away from you. So you could use the slope of the lines in a spectra to determine whether something was rotating and by how much. There used to be an exercise in the first year astronomy class at the University of Manitoba where you'd get students to actually calculate these speeds. I don't think they do it anymore. The other thing that spectrums can give us is the radial velocity. In other words, how much an object is moving towards or away from you. And this again involved the absorption lines. For instance, here is a modern day chart trying to explain this phenomena of redshift of the lines. In your reference standard, your laboratory standard, this might be the placement of these absorption lines. If you were to take the spectrum of a star that's moving modestly away from you, you'll notice that these lines are shifted towards the red end. A nearby galaxy might show a greater redshift, and a distant galaxy showing even greater redshift of the lines. Now, this is getting ahead of ourselves a bit here because this is starting to look like the work of Edwin Hubble. But Slipper did notice in his investigations, starting in about the year 1912, but being published in the year 1917, that the smaller and fainter spiral nebula that he was looking at had higher and higher radial velocities away from the observer, what we call recessional velocities. And here's his chart, his table that sums up all of the investigations he had made over these 5 years. And some of these investigations required a tremendous amount of effort on his part. First of all, he had to develop new photographic techniques to be able to photograph entire spectrums. Then he had to be able to have them sensitive enough to actually show up. But this still meant for very long exposure times. To get some of these spectra on these spiral nebulae, he had to expose the plate for 20, 30, 40, and as much as 80 hours to get enough data on it to be useful. This is his spectra of the Andromeda Galaxy. And this line across here and this line across the top are his reference standards that allowed him to calibrate what he was looking at in the spectra of Andromeda across the middle of it here. Now, the interesting thing is that these lines also show a very slight slope to them, indicating that the Andromeda Galaxy too is rotating. And when you look at a spiral galaxy, this is one of the immediate things that sort of springs to mind. This thing must be moving and twisting in some way. Slipper's data allowed us to be able to say that for certain the Andromeda Galaxy is rotating. His other work on the spiral nebula and the recessional velocities was also of use here too. Here is his table showing a few spiral nebulae, and these were the ones associated with Andromeda that seem to be coming towards us. They've got a negative value. Most of the objects he measured had recessional velocities. These objects were receding away from the observer, and some at startlingly high speeds. Here's one, and here's a few others that were receding from the observer at speeds of over 1,100 kilometers per second. The approaching ones, they were the Andromeda Galaxy, and one minor one here, which is M81. Now, most of what he saw was recessional velocities, and he was able to say with a fair degree of generality that the dimmer and smaller the spiral nebula that he was measuring, the greater its recessional velocity. He had no way of being able to tell the distance to any of these objects, but he was able to anticipate a great deal of what Hubble was going to demonstrate in about 10 years' time from his report. So from SLIPR, we have two very valuable results. One is that the spectrum can tell you about the rotation of objects, and we can tell its radial velocity towards or away from us. Both of these factors are going to become crucial when we get to the debate in 3 years' time. A little perspective on how the world looked in 1920, just as the debate was being given. Humanity had just emerged from one of its darkest and most senseless periods when patriotism and national bravado had resulted in one of the most ugliest periods in history, and a period where much of Europe was devastated and destroyed, which is part of the reason why so much of this story that I'm telling today is being told from an American perspective. It was World War I that was also directly responsible for the great pandemic of 1918, the H1N1 virus spread that resulted in somewhere between 50 and 100 million people dead. Also in 1920, it was the first year that American women were going to be allowed to vote. And seeing as they were able to calculate the value of Cepheid variables, I guess it was about time that that came about. Another very interesting insight into the mindset of the people in 1920 is this little postal or paper article about the American postal system. It was no longer accepting children, and this meant it was no longer accepting children as parcels. Apparently, up until this point, it had been common for parents wanting to send little Johnny off to visit grandma would just put a bunch of stamps on his jacket and send him through the parcel post, which is mostly handled by trains anyways. But in 1920, the Assistant Postmaster General pronounced that children clearly did not come within the classification of harmless live animals which do not require food or water while in transit. So at this point, the Postal Service decided to stop allowing children to be shipped through the mail. It was a very different world back then. I've mentioned George Ellery Hale on some previous slides as one of the innovators and people who were very good at motivating the construction of some of the new astrophysics style of observatories. He was also a member of the National Academy of Sciences And his father had left some money that sponsored a lecture series. So naturally enough, George was responsible for determining what a lot of these talks should be about. Being an astronomer, he wanted to have a talk about the latest and greatest exciting episode in astronomy, Arthur Eddington's proof and demonstration of proof of the validity of Einstein's general theory of relativity. Charles Abbott, who was the secretary of the National Academy of Sciences, didn't want to have anything of it. He thought that, first of all, the Brits will have done that subject to death, and it would be stale news by then. Plus, he wanted to have a talk on a subject that more than 6 people would even pretend to understand. His dislike for general relativity and Einstein was so great that he says he wishes science would progress to the point where it would banish general relativity beyond the 4th dimension from whence it came. And so he suggested other more palatable subjects, such as maybe discussing the reasons for the glacial periods that had recently been established. But that wasn't all that exciting an idea to hail. So he went with his alternative idea to have a discussion or even a debate about the idea of the island universes and the size and shape of our galaxy. And here's sort of the subject material that they came up with here. This is the description that they gave during the conference in April, where the title of the discussion was going to be, "How many universes are there?" This evening, 2 California astronomers will discuss the size of the universe and present their views as to whether or not there is only one or several universes. And that was decided upon as to be the general talk. Now, the interesting issue was, who were they going to get to give this talk? After some deliberation, they settled on these 2 astronomers. Harlow Shapley from Mount Wilson Observatory. Here's a picture of the Mount Wilson Observatory down here. He was a student of Henry Russell's and had just recently joined the staff at Mount Wilson. So when Hale suggested to Shapley that he participate in this debate, Shapley really couldn't turn his boss down and reluctantly agreed. Hubert Curtis was the main observational astronomer at the Lick Observatory at Mount Hamilton, east of San Jose, California. And he had just written a few papers defending and reviving the island universe theory as an interpretation of the spiral nebula. The Lick Observatory here at the top of Mount Hamilton had a few astronomers that were believers in the idea of the island universe, but it was Curtis's relatively recent defense of the subject that singled him out as the one that they should pick to give the side defending that. Shapley was a natural choice to give the interpretation along the lines that the spiral nebulae were part of the galaxy, because he had just finished issuing a series of papers in which he had shown that the galaxy was much, much larger than what had previously been anticipated. And he had used his studies of globular clusters, like the one shown here, and the variable stars within it. As you can see, stars such as these stars here that are flickering on and off. So this is like a time-lapse picture of some of the variable stars within a globular cluster. He had used the work of Henrietta Leavitt on Cepheid variables and refined and applied it to studying the globular clusters in an effort to determine the distances to these clusters. From this work, he was able to say that the Milky Way was much, much larger than we had ever anticipated before. Curtis, on the other hand, had been defending the idea that we have a smaller galaxy and a much larger universe. And a lot of this, surprisingly, was summarized in journals such as our own journal here. This paper was published in October of 20, but it was a summary of a series of talks he had given in 1919 on the subjects defending the interpretation of spiral nebulae as island universes. So this made him a natural for defending the opposite side in this great debate. The background and run-up to the debate sheds a lot of light on the actual characteristic of the debate. For instance, Carlo Shapley at this point, the boy wonder, he was about 35 years old when this debate took place, and an ambitious fellow. He was in the position at this point of trying to get a job replacing Edward Pickering here, who had just died the previous year, and who was the head of the Harvard Observatory. And here's a picture of Pickering amongst the Harvard computers, that group of women that was doing all that great work in trying to determine and process all of the data from all the telescopes involved in the whole Harvard Observatory school. Now, Curtis had already secured a position at the Allegheny Observatory in Pennsylvania. So his future was quite secure, and he didn't have to worry about his performance during this debate. Shapley, on the other hand, was not secure. He was hoping to get the job at Harvard, even though he was considered a little too young and green for the job. So he was very apprehensive and nervous about entering into a debate that might cost him his career. So there was a long group of discussions over exactly how this debate should take place. For one thing, he wanted it to be more of a discussion and a set of complementary papers rather than a knockdown, drag-em-out debate. Both of them agreed that they should exchange papers ahead of time to show the general trend in which they were going. But because Curtis was a very eloquent speaker, he had taught Latin and Greek and mathematics for many years and was known to have been quite the eloquent speaker. Shapley, who hadn't taught in a classroom situation or had done much public speaking at all, was very nervous, even though he was quite secure of his scientific position on the subject. So he tried to get the debate negotiated down. This is an actual copy of the telegram that was sent to Shapley at the time from George Hale, saying that the program committee of the National Academy of Sciences has proposed a debate between you, Shapley, and Hubert Curtis, and it's going to be done on such a date, everything like this. You're going to receive $150 for this. $100 of this, of course, you're going to have to spend on a train fare to get you from California to Washington. As luck would have it, the two of them ended up taking the same train together. Curtis's journey started in a stagecoach off of Mount Hamilton to get to the train station, where he met up with Shapley, and both of them rode to Washington together on the train. They both agreed not to discuss the subject matter, though, because they didn't want their debate or discussion, or whatever it turns out to be, to have a staleness to it. So they talked about other issues. But the one thing they might have talked about was exactly what issue they were going to talk about. Because as you'll see in the actual debate, the two of them were a little bit at cross purposes, and there really wasn't quite the contest that they had, that others had anticipated. And then there was always the issue of Curtis, who really thought that the issues that had been simmering for 200 years really need a proper airing out. And he thought that it'd be great for them to, yeah, we can cooperate and write complementary papers, but at some point we should go at each other hammer and tongs and really trash the heck out of each other's positions, you know, before we go off for drinks together at the end of the night. Because the two debaters came at this debate with such different agendas, it's not so surprising that it really wasn't that great a contest. The one thing to, jumping ahead a little bit here, the one thing to take away from the great debate was that it was neither great nor was it much of a debate. For one thing, Shapley gave kind of a speech, and a very introductory speech about the current understandings in astronomy versus a very slick presentation being given by Iber Curtis, where he used the latest in technology, the 19th century equivalent of a PowerPoint presentation, which involved lantern slides. Another odd aspect of the debate was there was no real true science reporters at this meeting. For some reason, they just didn't consider it to be that newsworthy, even though the debate itself was regarded in great symbolic terms as being a good hash out between two general camps regarding a very important issue. The end of the debate was monopolized by Henry Russell's defense of Shapley's position, because Shapley hadn't really done all that much to make the case against Curtis, whereas Curtis had presented a very technical paper that was really sharply critical of a lot of the stuff that Shapley was talking about. But even at this point, they were at cross purposes, because Shapley's presentation was so general and so timid in its proposals in some cases. Curtis's paper against him just seemed to be missing the mark, and they seemed to be talking at cross purposes. In the end, both sides were quite satisfied with their performances, and both had agreed that they were going to publish this at a later date in maybe a perhaps somewhat more fleshed out, polished version of things. Now, what's going to follow in my description of things is going to take into account both the actual presentation of that night and this document that occurred almost a year later, which had their written arguments out. And this was not just a rehash of what they had said that night. Both of them went home and formulated very long-winded official arguments as to what their positions were and what they thought the weakness of their opposition was. So what follows in my analysis of the great debate is not just so much the debate of that night, but of the entire debate argument that stretches up over their published paper of over a year later. The end of this situation has the result that Curtis does go off to the Allegheny Observatory and takes up the directorship there. Shapley does get to go to Harvard, but not directly. Here is one of the Harvard people who came to see him in Washington that night, and they had this opinion of him: a somewhat peculiar and nervous personality who lacks maturity and force and does not give the impression of being a big enough personality for the directorship position. The observers at this debate were much more impressed with Russell's defense of Shapley's position that occurred in the discussion after the presentations. And they really wanted Russell to have this job. Russell was one of the grand old men from Princeton University and thought that he would have been the perfect person to assume the directorship at the Harvard University. Russell wasn't that keen on the job because he thought that it was going to be a little too much work in general. But he was able to talk them into the situation of saying, well, if you want me, you got to take Shapley too. And they were quite happy to go along with that, saying, yeah, Shapley can do all the work and you can give all the perspective that it needs to be done. And they were quite happy with that situation until Russell decided, yeah, you know what, he didn't need that kind of clerical job to finish his career off on. And so he convinced them to take Shapley on in an interim position, which eventually turned into the permanent position that it was. But that's another story. Shapley spoke first at the debate, and his paper is the first in the series published in the journal talking about the debate. Essentially, he spent most of his time talking to his strength, his research project, where he showed that the globulars in our galaxy suggest where the center of our galaxy is and tell us how large it is. All of his work is based on the research done by Henrietta Leavitt that showed that Cepheid variables make for good standard candles that can be used to judge distance. The result of this is that he finds out that the sun is not at the center of our galaxy as was previously believed. Remember, several others, such as Cornelius Easton, had already suspected that, but wasn't able to prove it. The big point that Shapley wants to make is that his Milky Way is much larger, 300,000 light years, much larger than thought. And most of the other estimates at the time were anywhere between 6,000 light years, maybe 30,000 light years at the tops, but no need for anything larger than that. Shapley also regarded spiral nebulae as gas clouds. He had several reasons for thinking about them this way, mostly having to do with the way in which they were positioned, but we'll get at that in a second here. He also thought that the spiral nebulae had to be close by, but that they avoided the galactic plane, and we'll get into that in a sec too. And he was also bothered by the idea that Slipper's data and investigations had shown that there was a high velocity to these spiral nebulae, and there was no way to account for that if these were rather large, massive objects. One of his more pointed objections was that there was a nova in the Andromeda Nebula in 1885, and it's known as Nova S Andromedae. And if we were to believe Curtis's explanation of how far away the Andromeda galaxy would be, then this nova, being that far away and being as bright as it is, made it brighter than anything else they had ever seen. And these people had been noticing a lot of nova of late. They had noticed about maybe 24 in the Milky Way, and they had noticed a fair number in Andromeda itself, but nothing as bright as this. So if Curtis was right, and the Andromeda Nebula / galaxy was really as far away as he claimed, there was no explaining the brightness of this star going nova. Of course, what's really being anticipated here is that no one recognized that there was a different class of exploding star known as a supernovae. But that would require the work of Walter Baade and Fritz Zwicky another 10 years off in the future. He had three very pointed arguments against the idea of the island universe. The first is attributed to Frederick Sears, who somehow, and I read his paper, but I don't quite get it, calculated the surface brightness of the Milky Way galaxy and found it to be much less bright than the average brightness of the spiral nebulae, indicating that they were really two different kinds of creatures and not to be compared to each other. The other argument he gets from John Reynolds, who did work in terms of analyzing the luminosity across the spiral nebulae. And again, in another paper that I didn't quite understand, tried to argue that the luminosity curves of the spiral nebulae prove that they could not be made out of stars. And then there is the work of Adriaan van Manen, who showed that he could measure rotation in some of the spiral nebulae. And this last point here is the knockout punch. If this is established, then it's all over for the island universe theory. And Curtis also accepted that this point, if true, would be devastating to his interpretation of things. Here's a deeper look at some of Shapley's arguments. First off, here is his nice, neat, improved version of Henrietta Leavitt's work, showing a lovely consistency between the period and brightness of Cepheid variables. Keep this data set in mind when we go to Curtis's rebuttal. Also, this symbolizes his reluctance to regard the bright nova of 1885 as indicative or being tolerated by the idea that you could have this Andromeda Nebula at such a great distance. This chart here is a modern chart to show that we're still dealing with the same issue. This is a chart showing the entire sky, and it's graphing all the spiral nebulae, or as we call them today, galaxies. And notice this area through here, which was far more stark and defined in Shapley's time. This is what we call the zone of avoidance. And even the name is suggestive of an explanation for what they think is going on here. In this area, you don't find spiral nebulae. They're not to be found. This is also the galactic plane. It's as if the spiral nebulae are avoiding the plane of the galaxies and are only found near the poles of the galaxy. They are not found in the plane of the galaxy themselves. Now, here is Shapley's main claim to fame. This is his chart showing the location of all the globular clusters that he has measured Cepheid variables in and allowed him to get distances to. And we already knew the directions to each of these, so he was able to plot them in a three-dimensional sort of map. And if you look at the distribution of these globular clusters, you see most of them are to one side of the sun here. And this suggests that the center of the galaxy is to be found someplace in here, not near the sun. And when you take this distance measurement into account, you realize that you've got something of the order of about 50,000 light years between the center of the galaxy and the location of the sun. By the way, Shapley's measurement of a galaxy that's 300,000 light years across is a little bit more than what we think today. We think it's more closer to like 100,000. But the reasons for that are a little complicated, but the general idea is he wasn't really sure of all the Cepheid variables he was working with, and he had no account of the dimming factor that would be involved by any dust that happened to be in our galaxy. But to his other arguments, from Reynolds, he got the argument that you had a distribution of the luminosity of a spiral nebula that wasn't in accord with what a group of stars should give. Reynolds also argued that there's something really peculiar. If a spiral nebula, like this one, was just merely a collection of stars, it wouldn't show this color variation. Notice how the central part of this is much more orange and the arms far more blue. They were able to measure this back then, and this suggested that, well, no, galaxies just can't be a collection of stars, because a collection of stars would be the same color right across. There's something different going on in a galaxy than goes on in just a collection of stars, and this was one more argument for it being lumped in with the gaseous matter that was found in some of the other nebula, most notably the planetary nebulas. In actuality, what was going on here was that neither side was aware of there being two populations, two kinds of stars, very old stars, metal poor stars, and younger stars that were metal rich, that gave you this distinction of two different classifications of stars. Despite arguing for what we think of as the modern position as far as the island universe is concerned, the argument that Curtis put forward was regarded as sort of the traditional argument, mainly because he was arguing for a smaller galaxy. Not that he really needed it to be that small, but he just cited all the people before him that had come up with a very small galaxy, including some of Shapley's own earlier estimates where he had it much smaller than his most recent stuff. All he wanted to do for the most part was say that, hey, most of the people think it's much smaller, and if you think that having a really big galaxy means that our spiral nebulae have to be within it, that doesn't necessarily make any sense. And he brought forward many other different arguments on the subject. For instance, talking about the high recessional velocity that Vestal Slipher had determined for spiral nebula. This, he thought, made them a breed unto themselves and something that was not associated with the rest of our galaxy. He also took a look at most of the other spectra that the spiral nebula were produced. Again, a lot of these were done by Vestal Slipher, and so contradicted the earlier evidence of the Huggins, who had looked at the Cat's Eye Nebula and saw that it was an emission line spectrum, indicating that it was a gas. Now, what had happened was the Huggins were unfortunate enough to have picked the Cat's Eye Nebula, which sort of looks like a spiral, but in reality is a planetary nebula, and so wasn't a good counter example against the idea of the spiral nebula being external galaxies. And then he brought out the argument about if the Andromeda Nebula is close by and rather small, why does it have so many nova on its own? And he brought out the numbers saying there have been about 17 discovered in the last few decades, whereas the whole Milky Way had only produced about 24 of these things. So it came out to the point where there was so little difference in the numbers, why would we regard the Andromeda Nebula as being anything else but a commensurate rival to the Milky Way? And then he turned the tables on the nova question as well that Shapley had put forward. Remember, Shapley had said, well, there was that bright nova in 1885 that if the Andromeda Nebula was really that far away, this was a nova like we've never seen before. And yeah, Curtis would admit, yeah, it seems a lot brighter than any of the others we've seen. But what about the 17 that we have seen in the Andromeda Nebula? If the Andromeda Nebula is really as close as you would have it, why are these novas so dim then? And then he went forward with the estimate that Shapley had of 20,000 light years for the Andromeda Nebula, which was the largest of the bunch that they were discussing. If that was 20,000 kilometers away and all the other nebula were similar in size, but look so small in our sky, how far away must those be? And he did the calculation to show that some of those really tiny spirals must be as much as 20 million light years away for the smallest ones, if we're to assume that they are all pretty much the same kind of animal. So you'd either have to start speculating that spiral nebulas were all of a huge range of sizes, or that you had to admit that some of them were at really great distances. He also put forward the idea that there was a coherence problem in trying to fit these spirals into the story about stellar evolution. This has to do with the work of Hertzsprung and Russell, and a few of the other theoreticians that were trying to determine what was going on with the whole evolution and formation of stars and galaxies and nebula and everything else. So what he was trying to say was that the idea that you could apply the nebular hypothesis and start working with these spiral nebulas that no one was sure where they fit in. Did they come in at the beginning? Were they the end position? Were they something in between? He said, look, you're going to avoid all of this problem of trying to have a coherent description of things if you recognize that the spiral nebula have nothing to do with the nebular hypothesis that Kant put forward on the grounds of being the basis for solar system formation. And you didn't need to try and fit it into a Hertzsprung-Russell diagram either. So this is a very different kind of argument in some ways too. And of course, Curtis had to start talking about this. This is his, what we call by modern standards, his ad hoc hypothesis. He required the notion of dust to try and explain some of the problems that Shapley had put forward in his criticisms of the island universe theory. And yeah, then there was Van Manen. If Van Manen was right, then there was a serious problem with the island universe theory. And we'll get into that in a sec. All that Curtis could say at this point is, hey, I've tried to do what Van Manen did. I never got his results, and I don't believe his results now. Okay, this is a deeper exploration into Curtis's major points. First, notice these items here, which are very similar to the drawings or charts that we used to make Shapley's points. There wasn't so much an argument over the data that these people were using. It was the interpretation, the theoretical backing behind this data that they were arguing about. For instance, here is the chart of the scale of the universe that shows Shapley's Cepheid variable line. But instead of the neat, clean line that Shapley had, Curtis has added a whole bunch of other variables to it that were neatly left off of Shapley's fine-looking, neat, clean diagram showing a direct relationship between period and luminosity, which is the cornerstone of Cepheid variables. Curtis didn't like Cepheid variables being used in so strong a sense. He thought that maybe the method had potential, but it needed a lot more work before you were starting to use it strongly in the way that Shapley was using it. This is the little diagram trying to demonstrate the idea of the nova situation, and we've sort of talked about that already. The idea that, okay, yeah, there was one nova that was a bit brighter than it should be if Andromeda is at a great distance, but the 17 others show that it's at about the right distance if we stick it way beyond our galaxy, and that the other novas are then accounted for much better. This was also a big argument that Shapley used, but it goes way before him and what goes back to Simon Newcomb and such. And that has to do with that zone of avoidance. In other words, it's obvious that the spiral nebula have to have something to do with our galaxy because they avoid the center of it. They crowd towards the two poles of our galaxy. If they were really independent island universes, they would be spread out quite evenly across the entire sky. The fact that they are shown to not be found in the plane of the galaxy shows that in some ways our galaxy is influencing them quite strongly. It's not just some wild coincidence that they're separated away like that. And so what you have here is Shapley's point that, okay, these things are not found in the plane of the galaxy, and that means they're still somehow associated with the galaxy, but are just found near the galactic poles. Now, Curtis's only argument is, yeah, you know what? I think that my argument does say that they should be found evenly distributed throughout. And he actually did a whole bunch of work trying to find this. He did exposures double and triple the length in these areas here, trying to find spiral nebula to show that the zone of avoidance really wasn't such a zone of avoidance, but he failed and had to admit that, okay, this would be an argument against me, except that I've been observing a lot of galaxies, including ones like M104 here, the Sombrero Galaxy, which shows a very pronounced ring of dust around the edge of it here. And it's Curtis's contention that what we're seeing here is not the lack of galaxies, or not the lack of spiral nebulae, but just everything being obscured by a ring of dust around the edge of our galaxy. Notice he didn't talk about interstellar dust. He didn't talk about dust within the galaxy. Neither Shapley nor Curtis took that into account, and they should have. I mean, one of the reasons why Shapley's galaxy was 3 times the size of the modern galaxy is because he didn't take dust into account and had to place his globular clusters much further away because there was no dust to dim them. The only way he could get them dim was to put them at greater distances. But Curtis's point is, look, at the edge of our galaxy is probably a ring of dust, the way we've seen in so many other spiral nebulas, and that's what's causing the zone of avoidance. They're really there, we just can't see them. And then he went further to talk about the way in which you've got, this is a modern depiction of our sky. This would be the galactic plane here, and these symbols are for open clusters. Some of these are for planetary nebulas and other objects that are found in the plane of our galaxy. These bright blue dots up here are the spiral nebula, the galaxies, and they are found up near the poles. So these two pictures kind of reflect each other in that sense. And he was saying, look, everything else in our galaxy is found mostly in the plane of the galaxy. The one thing that isn't found in the plane is the one thing that isn't part of the galaxy. So he tried to turn the tables on everything that had been said in the, like they all agreed on the data essentially, but he just tried to give it a completely different interpretation. And then of course, I've brought forward something that's much closer to Slipper's original data set and showed that, yeah, if the bright, big spiral nebula had some recession to them, if you look at smaller and dimmer and fainter ones, you got higher recessional velocities. Now, he had no explanation for why that could be. All he could say was that we've got a situation where, look, if these things are all generally the same size, the ones that are further away seem to have that kind of distance to them. And of course, Shapley was bothered by the idea that these things would be large in general, because he says, to get these kind of velocities, these kind of recessional velocities, to move these huge spirals with that kind of velocity, and it's obvious that they're moving away from Earth for the most part, what physical process could have given those things that speed and that direction? Because remember, they're being directed away from our galaxy. So Shapley would come back and say things like, okay, look, you think you've got this relationship here, but what in our physics allows you to think that our galaxy could somehow push all of these huge objects that are so far away up and away from ourselves? So there was the crux of the point of the recessional speeds of the galaxies. And again, both of them agreed on the data, they just had different interpretations as to how far they should go with that. So in scoring the match, how does the numbers rack up here? It seems that Shapley was right in that the galaxy is much larger than they had thought earlier. He was definitely right that the sun is not at the center of this, and this is one of the issues that he is famous for to this very day in establishing that. And he was a good campaigner for the idea that Cepheids make for reasonable standard candles. There was a lot more sophistication involved in here, because it turns out there's two different kinds of Cepheid variables. There's also a problem of our Lyra variables being involved here. Lots of complications. But he was right on those big three issues of his. Now, Curtis was also right on several big issues. First of all, yes, from the modern point of view, the spiral nebulae are island universes. They are galaxies unto themselves, comparable to the Milky Way. He was right in that the rotation that von Manen thought he saw was not really observable. We're going to get into this a little bit more just before the end. And his ad hoc excuse saying, well, there must be dust out there that causes those objects not to be there, turns out to have been correct as well, even though the only explanation he could give for that was to say, hey, looks like other spiral nebula have dust as well. But he was already presuming too much. The debate was also entered into by Henry Russell, who almost ended up as being a third author in this because of his vigorous defense of Shapley's position in the original debate. But Russell did admit that from a stylistic point of view, Shapley had really lost the debate, didn't give a very sparkling performance compared to Curtis. And he came out with this remark at the end saying that Shapley needs to teach some classes in order to learn the gift of the gab. But I think the thing to take away from this is that even though they were right about their own areas of specialty. And this is what seems to be the thing to take away from this. When scientists are talking about their own areas, they're far more likely to be right when they're speculating on other areas where they are more likely to have things a little bit on the wonky side. Okay, now to address the elephant in the room. This is a picture of Adrian von Manen. He was an astronomer at the Mount Wilson Observatory, a very well-respected astronomer, who had done measurements into what he thought was proper motions within some of the spiral nebulae. And here's a couple of examples of his charts and work showing proper motion of different definable features in the spiral nebulae over a period of time. So what he would do is he would take a picture of the nebula and compare it to a picture that had been taken 10 years before, then put it under a microscope, very exacting tables to measure the motions of these galaxies as they rotated. And in these you can see the lines with arrows on them showing some of the motion that he claimed to have measured in each of these spirals. If he really was measuring rotation in a spiral over a period in as short as 10 years or 20 years, and he was able to show that this kind of motion was going on such a short time, that meant that these things had to be close. Because if these things were at the distance that Curtis wanted them to be, this amount of motion would be tantamount to these things moving much greater than the speed of light. And no one was willing to abandon the speed of light over what was going on in the rotation of these spiral nebulae. So von Manen's data, if it's accurate, was a death knell to the island universe idea. And his measurements, which were done over a long period of time, they were done very carefully. He even had other people come in and inspect it. This is Adrian von Manen here, and here he is again with Bertel Lindblad, who came over and repeated von Manen's work independently and came up with results not quite as pronounced, but at least in the same direction as von Manen's work. But what was happening here was something far larger. This is probably the greatest example of confirmation bias in science. And part of it has to do with some of the theoreticians. And that's where you've got people like the great British theoretician James Jeans, and Jacobus Kapteyn, who had done work talking about the way in which these spirals, which we knew were moving, we knew that from Slipher's results, but what was happening was we didn't know the evolutionary process that was going on in these spiral nebulae. But Jeans and Kapteyn had come up with ideas of how they thought things were moving. Van Manen was aware of all of this and somehow was not being able to put it aside when he made his measurements, or when he even had his measurements checked. For instance, in all of these, he had the motions of the little clumps of stars. They weren't individual stars for the most part. They were definable features. And he had most of the motion drifting out along the arms. If you take a look at the little vectors that he had drawn, you'd see that most of the motion of these things was out and around the spirals. And the spirals, and we could ask the question right now, which way do you think spirals are really rotating? And from Van Manen's measurements, they're rotating in a direction that the arms would be opening. So if this is an arm here, this whole arm would be rotating around and around in this direction, which oddly enough was opposite Slipher's measurement with the Andromeda Galaxy. Slipher had an arm like this arm. He had that arm spinning around in this kind of a direction, which is referred to as the winding up direction. So there was a direct conflict between Van Manen's data and Slipher's measurements, and somehow the two never came head to head over the issue. Van Manen kept carefully making measurements for over 10 years on this subject and never really seemed to question his results. Part of what was going on here was that his results fit in so well with the work of Kapteyn and Jeans. Their theoretical models had predicted motion along these lines, and Van Manen seemed to be delivering the data that they needed to confirm their studies. To make matters worse, our boy Harlow Shapley here was really good friends. They worked together at Mount Wilson and were really quite good friends, and they had a great conversation between the two of them about this data and what it would do to the last of those island universe believers like Knut Lundmark and Heber Curtis. So you've got a situation where certain familiarities and certain reputations having a lot more clout than they should in these circumstances. In 1919, Edwin Hubble comes back from his service in the war and some time spent at British universities to take up a position that was offered to him at Mount Wilson University years earlier. And he starts to work with the great 100-inch Hooker telescope at Mount Wilson to try and determine what's going on as far as the relative motion in these spiral nebulae are concerned. But mostly what happens is that a happy accident occurs where he actually resolves the whole debate that we've been discussing that had taken place over the last 200 years. And here's the kind of headline that announced it all to everyone. Another universe was seen by astronomers. So again, science writing has been bad for over 100 years. Anyways, Dr. Hubble had described the mass of celestial bodies 700,000 light years away. And this put an end to the debate. One of the things Hubble was interested in doing was trying to locate some of the nova and get estimates of their brightness so that he could finally make some distance determinations of his own to some of the larger spiral nebula. So here is his October 6, 1923 image of the center of the Andromeda Galaxy. You can see he's marked off one nova here. He's marked off another nova here that weren't on his plates from a previous date. And he had a third one indicated up here. But notice he's crossed out the word, the letter N, meaning nova, because he recognized that this was not a nova. This was actually a variable. So he set to work doing the measurements of it, got this kind of a light curve, classic Cepheid variable light curve, and realized that he now had a very good measuring stick to get a distance to the Andromeda Galaxy. He went straight to Shapley's papers and all Shapley's research, figured it all out at this point, and came up with that number of 700,000 light years. Andromeda was not in our galaxy, but was a galaxy unto its own. And this was demonstrated over time from his start in 1923 until the time he had sent his confident letter to Arlo Shapley in early of 1924. And after Shapley had read all of this and realized so much of it was based on his own information, he remarked to Cecilia Payne, who happened to be his office the day that the letter arrived, and said, "Here is the letter that has destroyed my universe." He recognized at this point that his own measurement techniques had been able to be used to demonstrate that the Andromeda Galaxy, as we can now call it, was much, much further away than he had argued for 4 years earlier. This was the least best kept secret in all of astronomy during this time. And when Herbert Curtis heard about it, this was his response. "As you know, I have always believed that the spirals were island universes, and Hubble's results seem to clinch this, though I myself did not need the confirmation." Not very magnanimous of Curtis at this point, and what's a little bit disingenuous on his part is the fact that they use Cepheid variables to prove his point. Remember, Curtis was deeply, deeply suspicious of using Cepheid variables to make these kind of distance determinations. But one of the interesting points in all of this was, okay, this result was announced January 1st, 1925, which is rather late for such an important discovery to be made. But it turns out that Hubble was very, very careful because of his colleague, again, Adrian von Manen. Von Manen's results still suggested that all of these guys were out to lunch. This cannot be the case. And von Manen had not been proven wrong at this point. Von Manen was still going ahead, making all these careful measurements that no one could quite duplicate, but it was a case of, look, I'm not going to come out with anything really strong until I'm a little more confident in my position. And he was actually forced to play his hand at January 1st. Henry Russell and a few of the other people were saying, when is Hubble going to publish on this issue? Because, you know, this is a huge event. He's going to win a particular prize worth $1,000 US at this point. How can he not take advantage of this just out of his hesitancy to cross his colleague Van Manen at this point? So what happens here is you've got a peculiar situation where everybody knew about a result, but there was no official published paper on the issue because Hubble was a little reluctant to go up against von Manen on some of this information. Now, about Hubble's hesitant claim here, we've got a few figures to bring into this argument. The first of them is John Reynolds, who was an amateur astronomer who had the gravitas of a professional astronomer and who had come up with a classification scheme of the spiral nebula that was very close to the system that Hubble eventually adapted. And they did collaborate and exchange information for quite some period of time. But here's the kind of thing that Reynolds put forward, because Reynolds wasn't a big fan of the island universe theory either. And he came up with this quote that says, "It seems it's safest to adopt an agnostic position as to the real nature of the spiral nebulae. there's always the possibility that they represent formations for which there is no analogies in the galactic system at all. And Reynolds held this position even past the point where Hubble had made the claim of this. Then there was the group of people, despite his unfortunate hair appearance, this is not the bad guy in our story here. That happens to be Knut Lundmark, one of the great campaigners, the champions for the island universe theory out of the University of Sweden. And he was one of the earliest people to go visit von Manen and check von Manen's results. And he was deeply critical of von Manen's results, saying, I can't get those kind of values that you think you're seeing at this point. Hubble also tried to get at von Manen's results. Bertel Lindblad was sort of supportive in the beginning, but ultimately went against it. The rest of, and this was becoming a crisis at the Mount Wilson Observatory because Hubble was getting quite agitated over this, and he really wanted to call out von Manen on the whole issue. So what happened was Walter Adams sent Walter Baade and Seth Nicholson, all of them, to check on the work of von Manen, and none of them got the same results. They realized that the minuscule amounts he was trying to measure over this 10-year period or 20-year period was so small that it was so subjective into systemic error that they couldn't for sure say anything was going on there. And they eventually, but very politely, regarded it as an example of confirmation bias, even though they didn't have that term at the time. But what you can say, in sort of a reverse of the old saw, you can say the idea that what von Manen suffered from was he had a belief in the theories of Kapteyn and genes, and was seeing what he needed to see as far as his results were concerned. But there was still a problem with Hubble's attitude about this. He really thought that he should trash the whole idea of von Manen's work before putting his own work forward, because he didn't want to have this debate happen over and over again with his stuff. But Walter Adams, as the director of the Mount Wilson Observatory, decided, you know, we don't need to be a bunch of jerks about all of this, and had this statement to say about Hubble, that this is not the first case in which Hubble has seriously injured himself in the opinion of scientific men by the intemperate and intolerant way that he has expressed himself. So you've got a situation where these people recognized that something was wrong, but wanted to approach it in a very particular way. So what can we take away from this episode that showed us our place in the big universe of things? First of all, there's a very interesting law that's due to a fellow by the name of Stigler's, and it's his law of eponymy, which is the idea of how things are named. And it's a very simple statement. It's that no scientific discovery is named after its original discoverer. And hopefully when you think about the people that I have mentioned in this talk, such as Swedenborg and Thomas Wright and Henderson and Cornelius Easton with his anticipation of the position of the sun, Vesto Slipher anticipating so much of the work of Hubble, De Sitter, we didn't really get a chance to talk much about him, who was able to anticipate so much of what Hubble tried to prove later and was combining it with the work of Einstein. He was taking Einstein's work forward to give explanations for some of the results that Hubble came up with. Oddly enough, Hubble never finished or quit calling the spiral nebula. He never referred to them as galaxies. He always referred to them as nebula and never took the conviction of his own results. And then, of course, there's Knut Lundmark, who had campaigned for so much of this all the way through and was, largely ignored and had to fight a lot of these other people, such as his great arguments with Hubble that we don't get a chance to get into. The other thing that we should take away from this episode of science is the way in which the data isn't something plain and simple for these people to argue over. This is not the sort of, if the theory says this, then this evidence will result. We find the evidence, therefore the theory is true. Arthur Eddington came forward with this version of his reluctance to believe in that style of science. And he said it this way: do not put over much confidence in the observational results that are put forward until they are confirmed by theory. In other words, the data can speak with many voices to many different theories. And unless you have it within a theory, you're not really sure what you are looking at. And that's this idea that philosophers of science try to make a great deal of. And that's the idea that data is not pure or objective. It is always, in some sense, theory laden. And to conclude this whole talk at this point, sorry for running so long on this, here is a picture taken by the Hubble Space Telescope of Hubble's greatest claim to fame. Here's the galaxy as we usually see it in our photographs. Here is the picture frame that showed up in Hubble's historic picture of October 6th, showing the variable star, which is known now as V1. And here's the Hubble Space Telescope, named after Edwin Hubble. And here is a picture of that variable that still exists today and is blinking away, looking very innocent like many other stars of its time, and yet serving such an important purpose. And that concludes today's talk.
Okay, well, thank you, Jerry. That was very interesting. A little long, but thank you, Jerry. I appreciate that. That was really excellent. I guess that will conclude. Yes, we should have applause here. Thank you, Jerry. Excellent. Everyone's clapping here. What I'm going to do is I'm going to forego the virtual Boston pizza thing. It's getting kind of late. My computer's going to take some time in processing this recording that I did, and I'll post it up on the website soon. So what I'll probably will do is I'll do a informal meeting maybe next weekend. We'll see. So again, I just want to say thank you to the panelists. Thank you, Jay. Thank you, Jerry. Thank you, Darren, and thank you, Scott, and thank you, Michelle. All right, so that'll be in.
Before you shut it down, Brian, can I just maybe throw a generic question that maybe we can do a follow-up meeting on at some point?
Yes.
Because Jerry's talk about this data is very profound in a way. I mean, looking at how everything's, the data is somewhat laden with theory laden, basically. And I wonder if we're starting to see the same kind of 100 years later now with dark matter and dark energy, whether or not some of the data that we're seeing is reflective of, we're seeing this kind of same type of debate kind of emerging. And that might be an interesting little discussion and chat sometime with people like Michelle and some of the astrophysics folks. And it would be kind of an interesting one to talk about. So I'll just put a pin in that. I don't want to drag it out any longer. It's been pretty late, but maybe that's something to discuss either on the forum off site, or maybe we can host a little Q&A kind of roundtable down the road. I think it'd be really interesting. Thanks.
Yeah,
guys.
well, yeah, okay, no, thank you, Darren. That was very nice. Yeah, we'll do an informal virtual Zoom meeting again, but it'll be just a meeting, and people can maybe post their questions. So I'll try to set that up a little later, maybe next weekend. But yeah, it's getting kind of late. It's going to probably take my computer probably a half hour to process this whole recording. But like again, okay, I want to thank you, everyone. So that will adjourn April's meeting. All right, I'll see you guys next time soon. Thank you.
Cheers.